মিনাজ, ওনাকে তো লিংক পাঠানো আছে। মিনাজ,
হ্যাঁ ম্যাডাম, সবাইকে লিংক পাঠানো আছে। সব স্পিকার আর চেয়ারকে লিংক পাঠানো আছে।
আচ্ছা।
পৌলমী আছেন?
16 তারিখে লিংক পাঠিয়েছি।
পৌলমী ম্যাডাম, যদি ওই রেকর্ডিংটা আপনি শুরু করে দেন, মানে সময় মতো।
10টা 20 তো 10টা 30 দেখি কখন জয়েন করেছে।
পৌলমী করুক, প্যারালালি আমিও চেষ্টা করছি।
হ্যাঁ, মানে ওই টাইমে না মানে ভুল হয়ে যায়, মানে
হ্যাঁ হ্যাঁ, মানে পৌলমী করুক, আমিও এখান থেকে আছি, আমি রেকর্ডিং অন করে
কেউ না কেউ একজন করে দেন আর কি।
কেউ না
মোজাম্মেল
কেউ
এসে গেছে।
যাদের, হ্যাঁ হ্যাঁ, মোজাম্মেলও আছে। আমি বলছি যে
জিসুট
যারা
অ্যাকাউন্ট
ইনস্টিটিউট, হ্যাঁ জিসুট অ্যাকাউন্ট যারা ইউজ করছে, কেউ না কেউ করে নিতে পারে।
দীপালি দি,
হ্যালো,
আপনার কাছে ওনার ফোন নাম্বার বা কিছু আছে কি, বা হোয়াটসঅ্যাপ নাম্বার বা কিছু?
হোয়াটসঅ্যাপ নাম্বার তো নেই। হোয়াটসঅ্যাপ নাম্বার নেই। ফোন
মেসেঞ্জার
নাম্বার, হ্যাঁ ওনার একটা ফোন নাম্বার আছে, সে ফোন নাম্বারটা দেবো একটু?
দেবো,
দাঁড়াও,
মানে আপনি ফোন করে একবার যদি দেখেন আর কি, ফোন করে একটু কন্ট্যাক্ট করে দেখুন যদি। কারণ আর 6 মিনিট বাকি আছে। Good morning, sir. Good morning, Professor Liu. হ্যাঁ বলো। Good morning, sir. Good morning, Professor Liu. Can you please unmute your microphone? We can't hear you now.
Okay. Can you hear
Yes,
me now?
it's okay now. It's okay now. Good morning, sir.
Okay. Good morning. Good morning. Okay.
This is
so. Yeah, please.
yeah. So let me start the session.
Okay.
Actually, we are 3 minutes ahead. The session is scheduled at 10:30.
Okay.
So let's wait for the participants to join. We'll start at sharp at 10:30 a.m. Indian Standard Time. So
Okay.
we have 2 more minutes in hand. After that,
Okay.
we'll start.
Okay. All right.
Okay.
So can you see my my screen?
Yes, we can see your now. We can see your yeah. You can see your screen.
Okay, that'd be great. How about a PowerPoint?
Yeah.
You can do that as well. Wait a minute.
Sorry.
Can you hear this PowerPoint?
Yes, yes, we can see the PowerPoint. It's in slide mode now. Yeah.
Okay, that'll be great.
Fine.
That'll be great. It seems like there is some delay of the voice transmission, right?
Yeah, voice is also fine. It's okay.
Okay. All right. Okay. If I can start, just let me know. Okay.
Yeah, in 1 minute we are going to start.
Okay.
So how many participants do you have? We have around how many? Let's see. 34. Professor Liu, your PPT is in slide mode. You can put it in full screen also. I mean, that will be a larger screen. So.
Oh, okay. All right. I got it. Yes. Yeah. Is it okay?
Yeah, yeah. That's perfect.
Okay.
So it's 10:30. Good morning, everyone. So today we are on the third day of our international webinar, Advances in Electronic, Optoelectronic, Photonic Materials and Devices. In the last 2 days, along with the inaugural session, we had 5 technical sessions covering many different aspects of this broad area, like nonlinear optics, photonics, optoelectronic devices, fiber optic sensors. Also, we had talks on the topics ranging from basic fabrication tools like CVD to characterization techniques like photoluminescence measurement at very high magnetic field. Now, today in the morning session, we are going to start the 6th technical talk on synthesis and characterization of thermoelectric materials. This talk will be delivered by Professor Chia Jai Liu from Changhua University of Education, Taiwan. We are thankful to Professor Liu for accepting our invitation and getting some time out of his busy schedule to illuminate us with his recent research work. So this session will be chaired by Professor Deepali Banerjee from our Department of Physics, IIEST Shibpur, India. Professor Banerjee joined our department in the year 1995. She is working in the field of experimental condensed matter physics for more than 3 decades. Her work is emphasized on electronic transport properties of materials. She has completed many sponsored research projects funded by different government agencies of India and published many research articles in the journals of international repute. She has also produced a good number of PhD students. Now I invite Professor Banerjee to chair the session. Professor Banerjee, please take over the chair.
Thank you, Minaj, for a nice introduction.
Welcome, ma'am.
I welcome you all today and a very good morning to all of you, including Professor Chia Liu. I'm very much delighted to see you here on this virtual platform. Now, it is my task to introduce you that you are a distinguished professor of National Changhua University of Education, Taiwan. Professor Liu, he received PhD from Johns Hopkins University, USA, worked as a postdoc at Southern Illinois University, as a visiting scientist at Superconducting Research Laboratory, Japan, as a research fellow at Victoria University, Wellington, New Zealand. His current interest is developing novel material for green energy generation. He has collaboration with Medical University, Vienna, Istanbul Technical University, Turkey, University of California, Clemson University, both in USA, Tarbiyat University, Iran, University of Ibadan, Nigeria, has several publications of the order of 133 and 4 editorial contributions. Now we see that for years to come, the increasing energy demands are anticipated. The search for material to meet the energy need for the civilization in a sustainable way is indispensable and challenging. As we have heard from Professor Shomit Roy in his yesterday's lecture, that we need, that is our consumption of power is of the order of several terawatt. And at the same time, several terawatt of power is wasted during the power generation in the form of heat to the environment. Some materials have special property to convert this waste heat into electricity via Seebeck effect. And the same materials can also be used as refrigerant or coolants via Peltier effect, which can replace, these materials can replace chlorofluorocarbon, which are the popular coolants and refrigerant materials, because these chlorofluorocarbon has a detrimental effect on the layer of ozone protecting us in our upper atmosphere. So these materials are regarded as green energy materials. what are actually these materials, how they are synthesized, and how they are used for application, we will hear from Professor Xia Liu. Okay, Professor Xia Liu, please.
Okay, thank you. Good day, everyone. Thank you.
There is a small announcement to everyone. Professor Liu, just one announcement that if you have any query, the participants, if you have any query, put your questions in the chat box. And we are streaming this Google Meet through our IIEST Live YouTube streaming link. So the participants who are watching the YouTube streaming, you can also ask questions through the comment box. Our representatives are there. They will PhD students will take your questions and put in the chat box of the Google Meet link. So you ask your questions in the chat box. That's all. Thank you. Professor Liu, please start here.
Okay, all right. Okay, good. Good day, everybody. Thank you for the invitation by Professor Banerjee. I'm honored to have the opportunity to present my research work on thermoelectric materials. My name is Jiaji Liu, and I work in the National Tsinghua University of Education, Taiwan. Thermoelectric material can be used in fabricating devices for producing electricity as generator or for cooling an object as a refrigerator. Today, I'm going to talk about the synthesis and characterization of these energy materials. Before my talk, let's take a look at our locations. Here's your campus, and there is mine. It seems that we have a similar latitude. Our location seems to quite a distance, but not much about the internet. This is a lake in our small campus, and I'm now sitting in the room within this building. First off, I will begin with a brief introduction of thermoelectric phenomenon, application, and the criteria of potential thermoelectric materials. I will focus on the hydrothermal synthesis of P-type bismuth antimony telluride and room temperature synthesis of N-type copper selenide. If the time is allowed, I will show some results on the work on P.PSS film. First off, I will begin with a brief introduction of thermoelectric phenomenon. Thermoelectric phenomena include 5 effects. They are the Seebeck, Peltier, Thomson, Joule, and Fourier effects. These 5 effects come all together in a thermoelectric circuit. And this is the thermoelectric circuit, which is composed of 2 dissimilar materials with their ends connected to have 2 junctions. When electric current flows in this circuit, then heat will be generated, and this is the Joule effect. When there's a temperature difference between these 2 junctions, then there's a heat conduction between these 2 junctions, and this is the Fourier effect. About the Seebeck effect, Seebeck effect is the thermal EMF generated when there's a temperature gradient between these 2 junctions. Therefore, the Seebeck effect can be used to generate electricity. We define the Seebeck coefficient as dV over dt, and Seebeck coefficient also called thermal power. And this is a cartoon to show this effect. If the majority carrier of the material are electrons, since particles move from the hot end to the cold end, from the hot end to the cold end, so there will negative charge would accumulate at the left-hand side, and the positive charge at the right-hand side. Then we have an electric potential developed between these 2 ends. The Peltier effect is the reverse phenomenon of the Seebeck effect. When you apply electric current through this circuit, suppose the direction of electric field goes from right to the left, then the negative electron will be driven to the right-hand side. Then they will have more energy and evolve heat. Since the left-hand side loses energy, and its temperature will get colder and will absorb heat. As seen in this definition, the Peltier heat Q dot is proportional to the applied current, which is different from the Joule heat being proportional to the square of the applied current. And the pellet heat is related to the direction of the applied current, while the Joule heat is not. See, when you reverse the electric field, the direction of the electric field, then the cold side will become the hot side. The hot side will become the cold side. Okay. Okay, now the Thomson effect. Thomson effect is different from the above two effects. It does not need to have two dissimilar materials. As long as the presence of both electric current and temperature gradient along a single conductor, they will have heat evolution absorption along the length of the single conductor. Whether the cross-section of the conductor absorb heat or evolve heat depends on the relative size of the Joule heat right here and the Thomson heat. If the Joule heat is larger than the Thomson heat, then you would evolve the heat, vice versa. And this is the illustration how thermoelectric generator works. Here's a single device, single pair of a device made of P-type and N-type materials. As the temperature gradient develop from top to the bottom, both electrons in N leg and holes in P leg will move to the cold side, and then the seeback voltage develops in this circuit, just like a battery. And this is the illustration how thermoelectric cooler works. When the P leg is connected to the negative end of the battery and N leg to the positive end, both the holes and the electrons will be driven to the right-hand side in this device. Since holes and electrons carry energy, and therefore the right-hand side would evolve heat and the left-hand side will absorb heat. The left-hand side therefore can cool any object attached to it. And this is one of the commercial thermoelectric modules, which has multiple pairs of thermocouples. And the number of thermocouples depends on the size of the module. The typical size right now is 3 centimeter by 3 centimeter, 4 centimeter by 4 centimeter. You cannot get to too large size of the module because the module could be bent when you heat it up. Okay, then what is the criteria of the potential thermoelectric materials? The value of dimensionless figure merit ZT is used to evaluate the potential of a thermoelectric material. ZT is defined as the power factor divided by thermal conductivity, where the power factor is the product of electroconductivity and the square of thermal power. High performance thermoelectric material requires higher ZT value. That is, we need to have high electroconductivity, large thermal power, and small thermal conductivity. Unfortunately, these three parameters are independent. As you can see from this plot, the higher conductivity is accompanied by the small thermal power. As you can see, the material with moderate carrier concentration will have an optimal ZT value, such as semiconductors. Besides, the Weidemann-Franz law governs the relations of electrical conductivity and electronic thermal conductivity. If we enhance the electroconductivity of a material, it would also increase its electronic thermal conductivity at a given temperature because the Lorentz, this is called Lorentz constant, which is a constant. So what it means is that if you attempt to enhance the electrical conductivity of a material by doping to increase its carrier concentration, at the same time, you will increase its electronic thermal conductivity, which seems to make your efforts in vain. Fortunately, we can manipulate the lattice thermal conductivity to reduce the total thermal conductivity despite the increase of electronic thermal conductivity. To reduce the lattice thermal conductivity, you can make nanostructure material to expand thermal limits and beat the alloy limit and the amorphous limit in thermal conductivity. There's a good reference listed here, published in Nature Today. You can take a look at this. These are two examples of beating alloy limit As you can see in this plot, the thermal conductivity of the silicon germanium alloy nanowire is lower than the film, lower than the silicon germanium alloy film at this temperature. Take a look. Therefore, the lattice thermal conductivity can be further reduced by scattering long wavelength phonon by nanostructuring. In another example, the bottom panel shows the thermal conductivity of indium gallium arsenide embedded with eurobeam arsenide nanoparticle, which is lower than that of indium gallium arsenide without any nanoparticle in it. And this is because nanoparticles scatter mid to long wavelength photons and further reduce the lattice thermal conductivity. Take a look at the temperature here. The reduction of the thermal conductivity at this temperature compared to here. So this is a longer wavelength, and this is a mid wavelength of the phonons. And this view graph shows the example of beating the amorphous limit. Amorphous solid limit the mean free path of phonon to a few lattice spacings, and therefore have a very low thermal conductivity, which is called the amorphous limit. As you can see from this panel, the thermal conductivity of tungsten alumina nanoleavenite with a high interface density is lower than the theoretical minimum lattice thermal conductivity of the aluminum oxide and the thermal conductivity of the constant aluminum oxide predicted using diffusive mismatch model. Here, these two lines are the theoretical curve, and you can see the experimental data can beat the amorphous limit. Therefore, material with a high interface density can beat the amorphous limit. Besides, we can try to increase the porosity. As you can see, the blue dots has a larger porosity and compared to the red square. Okay, so if you make the material porous to some extent, not to deteriorate the electrical conductivity. On the other hand, you can reduce the thermal conductivity to have a better thermoelectric material performance. In addition to the nanostructuring, introducing the point defect plus the grain boundary scattering would be a panoscopic approach to the scattering of heat-carrying phonons on all relevant length scales. An example of this approach is the sodium doped lead telluride with point defects, nanostructuring, and the mesostructuring. In this plot, the blue solid line is the lattice thermal conductivity for pristine lead telluride. One solid line for doping lead telluride with sodium, which introduce point defect and reduce lattice thermal conductivity. Adding nano-sized strontium telluride into the sodium doped lead telluride, the green solid line is nanostructuring, which further reduce lattice thermal conductivity. If we add micron size strontium telluride into sodium doped lead telluride, the red solid line is mesostructuring and further reduce lattice thermal conductivity in the high temperature region. As you can see from the right panel, this approach has significantly enhanced the Z value from 0.7 to 2.2. Take a look at here. This is 0.7, it's around 2.2. To sum up, short wavelength phonon can be effectively scattered by defects or solid solution. Mid to long wavelengths can be scattered by nanoparticles. Even longer wavelengths can be scattered by high density interfaces, which means the grain boundary. Another example is the case of commercial bismuth antimony telluride alloy, which holds the record of ZT equal to 1 for about 50 years before the year of 2009. The ZT value is enhanced to be greater than 1 due to a decrease of thermal conductivity by nanostructuring. Okay, now the power factor. To enhance the power factor in the expression of the ZT, we can take advantage of number of degenerate carrier pocket in the band structure. As you can see here in the expression, the power factor is proportional to the weighted mobility represented by capital U. And in this formula, the m star is the density of state effective mass, and the mu is the non-degenerate mobility of carriers. The number of degenerate carrier pocket, MV, is proportional to the m star. Therefore, the larger value of the degeneracy, MV, has higher power factor. As you can see here, MV can be increased by doping, or the temperature, see the right panel, can be increased by doping or the temperature to shift the relative position in energy for different carrier pockets. At this temperature, this carrier pocket, two carrier pocket merge, and the MV is almost 2. So therefore, your power factor is enhanced. For thermoelectric device, from this expression, higher ZT leads to a higher efficiency. Also, larger temperature difference between hot and cold ends, the efficiency is larger according to the Carnot efficiency limit. You may have a temperature difference of about 500 degrees C. One would expect an efficiency of 30% for a thermoelectric generator if the ZT of the material falls in the range between 2 and 3. So this is the target for thermoelectric researcher looking for. The size of the efficiency will be comparable to the solar photovoltaic cell. And this is the Voyager 1 using radioisotope thermoelectric generator as its power source in deep space exploration. T module can also make to power a watch like this via the body temperature. And the Voyager 1 was launched in 1977 and now have launched the interstellar space and continue its unique journey through the universe. Just a minute, there's some problem here. Okay. Let me restore it. Yeah. Okay. Here is the radioisotope thermoelectric generator installed at the Voyager 1. It has been 43 years now and is still working. Therefore, the thermoelectric modules are very durable. And also, if you, once again, come on. Okay, sorry. When you go out for a picnic, you can also charge your cell phone with the thermoelectric generator, which also used to provide the electric power for Mars rover. Thermoelectric module can also be used to provide thermoelectric cooling. It is portable. Okay, you can use it as a refrigerator when you go out. And the heat source of MMRTG is from the heat of plutonium radioactive decay. And if you consider solar energy, there's a 42% of the solar energy can be used to provide a heat source for the thermoelectric generator. So you can use wavelength separator to utilize the solar energy for both solar cell and thermoelectric applications. Miniature T device can be made into a low power for medical applications. You can have say like here, 111 microwatt. People also think of using thermoelectric module to harvest solar energy from the exhaust gas of a vehicle. And this is the prototype made by Volkswagen, also by BMW. And TG is located here. This is the TG, thermoelectric generator. And also, TG is very suitable in mountain and a remote location where do not have the power plant. Here as well. Okay, now let's go to the synthesis. There are 12 principles in green chemistry for synthesis. In the 6th principle of design for energy efficiency for green chemistry, chemical processes are suggested to conduct it at the ambient temperature and pressure for minimizing the energy requirement on environmental and economic impacts. Our objective for synthesizing thermoelectric is to follow this guideline using less energy consumption. Here, I will simply use a temperature pressure map to compare the hydrothermal synthesis with the other material processing technique. As you can see from the map, when compared to the solid-state reaction, here, the solid-state reaction, and the melting process there, and these two processes are commonly used to fabricate thermoelectric materials. If you consider the environmental load, the hydrothermal method is obviously friendly to the environment. Hydrothermal synthesis sitting here. So using the hydrothermal method to synthesize the material has the following advantages. Number one, hydrothermal methods usually take place in a closed system at low temperatures. Hydrothermal method can provide an energy saving and environmentally green way for fabricating nanomaterials. And also, you can exercise the thermodynamic variables such as reaction temperature, concentration of reactants, and the various additives to have effects on reaction product. I'm going to show you for the first two thermodynamic variables in a few minutes. And this is the typical autoclave for hydrothermal synthesis. You put a sample in a Teflon cup and then put into the autoclave. Okay, now let me move to my first material system, antimony doped bismuth telluride, which was synthesized using hydrothermal method and achieve a ZT equal to 1.65 at 290 K, and with this antimony content equal to 1.55. In the synthesis, we use the bismuth chloride, antimony chloride, and tellurium as the starting material in the presence of EDTA, KOH, and the sodium borohydride. And the sodium borohydride acts as a reducing agent, and the reaction temperature occurs between 140 and 160 degrees C and held for 36 hours. And when you do the antimony chloride, because it is hygroscopic, so you have to try and error to get appropriate amount of the antimony chloride. Instead, you can also use the antimony, but the results are a little bit different. Okay, there are three thermodynamic variables we use to study their effects on hydrothermally synthesized products of doped bismuth telluride alloys. And this is the how the molar ratio of sodium borohydride over tellurium affects the X-ray diffraction patterns. As you can see, the shoulder around 35 degrees, whereas the have a refraction peak of 0.15. You can see the shoulder vary with the ratio being used in the synthesis. The ratio is 4, 3, 2, and 2/3. And you can see the index refraction peak arises from the antimony doped telluride, and the symbol asterisk indicate the asterisk symbol indicates the peak belong to the second phase of tellurium. So there's always presence of tellurium as the second phase in the synthesis. Also, it turns out that the molar ratio equal to 4 has the best thermoelectric power factor and also the best ZT value. Okay, from the this AFM image, you can see the hexagonal platelet, and the thickness is about 30 to 50 nanometer. Okay, and for consolidating the powder, people often use cold pressing and sintering nanocrystal under argon atmosphere, or use hot pressing, or use spark plasma sintering to consolidate the synthesized powder. In our work, we adopt the evacuated and encapsulated sintering technique. This is a setup for this technique. We put the powder in either the coarse tube or the Pyrex tube, and then evacuate it and then seal it. So this is what I said, evacuated and encapsulated sintering technique. For transport property measurement, we use the 4-probe technique to measure the electrical resistivity. Use steady technique to measure thermal power, this one, and use transient brain source technique to measure the thermal conductivity. This is the sensor. It's quite expensive. It cost me about maybe like let me see. Well, in NT dollars, like $30,000 NT dollar. So that means about 1,000 US dollars. This is quite expensive. Okay, in the technique, the sample was the sensor was sandwiched between two pieces of the two pieces of materials. Okay, and this the left panel is the setup for low temperature measurement of electrical resistivity and thermal power, and the right panel is the hard disk thermal constant analyzer for thermal conductivity measurement. Here is the hard disk thermal constant analyzer, and we have low temperature measurement. We just insert the sample holder into the liquid nitrogen container, and then we can measure the thermal conductivity as a function of temperature. And here is for high temperature, they can go up to like 700K or 800K. Depends on your need, and also depends on the life of your sensor. Okay. This plot shows the effect of reaction temperature on the actual diffraction patterns. As you can see, the shoulder of 015 peak, it is a little bit different from each other. And if you take a closer look, it's a little bit different. And they do have effect on the transport property, even though the actual diffraction doesn't show much difference. And also you can see the relative intensity is different. From this view graph, you can see the effects of the reaction temperature on the transport property from this view graph. As compared to the red line, the sample was synthesized at 140 degrees C. The 160 degrees C material has smaller electrical resistivity and also smaller Seebeck coefficient, but higher thermal conductivity. I would also like to point out that this 140 degrees C material has relatively large thermal power compared to those with similar composition fabricated with other methods. In general, the thermal power falls in the range between 200 and 250 microvolt per Kelvin. Here we have the value somewhere between 270 and 280 microvolt per Kelvin. As I said, tellurium exists at the second phase in the synthesized materials. The enhancement of thermal power could be due to the energy filtering effect. Only carrier with higher energy can go beyond the energy barriers posed by tellurium nanoparticles and contribute to the thermal power. So the thermal power will be bigger. Since thermal power is a measure of the heat per carrier over temperature, that expression here, therefore, the system has more energy per carrier, and thus will have larger thermal power. And this is similar to the case of tellurium nanoparticle embedded in the bismuth antimony telluride film. As you can see from the right panel, higher TC concentration in the film leads to higher thermal power. Okay, this plot shows the effect of antimony content on the electrical resistivity. As you can see, the antimony content with X equal to 1.55 has the lowest resistivity among this series of materials, and the X and the X equal to 1.5 has the lowest thermal power, but X equal to 0.155 material catch up. I'm sorry, the X equal to 1.5 has the largest thermal power, but the X equal to 1.55 material catches up and they have about the same magnitude as the 1.5 material between 250 and 300K and reach about 280 microvolt per Kelvin. As a result, the X equal to 1.55 has the largest power factor. It's about 26 megawatt per centimeter K squared. And also, we made another, because the sample seems to be has a pretty good result on the power vector. So we made another batch of the sample. The plus shows the reproducibility of the electrical resistivity and thermal power for two samples made in different batches, and they look quite consistent. And both the x equal to 1.5 and 1.55 samples exhibit quite low thermal conductivity, with the value of 0.36 and 0.4 watt per meter Kelvin. And as you know, the typical value for this type of material made by melting process is about 1 watt per meter Kelvin around room temperature. So these two values are quite small. And this low thermal conductivity can be attributed to its nature of nanostructure with different size of grain boundary. And you can see the grain boundary also randomly arranged. As a result, the ZT value reaches 1.65 and 290 K for the x equal to 1.55 materials. Okay, summary on the series of bismuth antimony telluride. We synthesize the material by hydrothermal synthesis, and we can get a ZT 1.65 at 290 K and 1.75 at 270 K. And this is about 60 to 70% enhancement of the commercial state-of-the-art material around room temperature. And the significant ZT improvement should be attributed to much reduced thermal conductivity. Okay, since bismuth antimony telluride is a layer structure, and there's a large spacing of between these two, about 2.6 angstrom between two layers of tellurium-1, one could then expect an isotropic transport due to the weak van der Waals bonding between two layers of tellurium-1 along the c-axis, c-axis along this way. In characterization of the anisotropic structure, we press the hydrothermal synthesized nail powder into a cuboid like this, and shine the X-ray at different faces of the cuboid. We designate the Z phase as the phase perpendicular to the uniaxial pressing direction. The other two phases, X and Y, are parallel to the pressing direction. As you can see from this X-ray diffraction pattern, the refraction period of 0.15, these are two largest peaks, 0.15 and 1.010, for Z phase have similar intensity. But the other two, you can see that have different intensity, relative intensity, indicating an isotropic structure in this cuboid. Also, the from the electron resistivity measurement, you can also see the Z phase. The electrical, if you flow the electric current along the Z phase, and then you will get the higher resistivity than the XY phase, which we measure by applying the electric current along the X phase or Y phase. However, the thermal power shows less anisotropy, and this is quite amazing. Their magnitude are similar to each other. As a result, the power vector for X and Y phases are larger than that of the Z phase because they have larger electrical conductivity. The thermal conductivity also exhibits anisotropy in that the Z phase has larger thermal conductivity with the value about 0.48 watt per meter Kelvin and 0.41 watt per meter Kelvin for the other two phases. So it's like electrical resistivity. X and Y phase shows similar size of thermal conductivity. Okay, so as a result, we got the ZT 1.59 for the X phase, 1.49 for the Y phase, and 1.11 for the Z phase. Okay, so this is about the bismuth antimony telluride. Okay, let me move to the second material system, energy efficient synthesis of tellurium doped copper selenide. That is just published in ChemSysChem. This work has selected as a cover feature is shown here. Copper selenide has a simple chemical formula, but complex atomic arrangement. It is also well known that copper selenide undergoes structural phase transition from monoclinic low temperature alpha phase to phase center cubic high temperature beta phase at about 413 K. And due to its low electrical resistivity, large thermal power, and low thermal conductivity, copper selenide is one of the potential thermoelectric materials. Among the recent reports, copper selenide exhibits a ZT of about 1.4 to 1.8 at around 800 to 1000 K. However, the reaction temperature is 1423 K for 12 hours in vacuum, and then slowly cooled down to 1040, and 1073 K for 24 hours, and held there for 7 days, followed by consolidating using spark plasma sintering at 710 K under a pressure of 65 megapascal. This process consumes a tremendous amount of energy. As you can see that it does not make sense to fabricate material used to generate electricity and consume a lot of energy. And this does not really follow the sixth principle of green chemistry. As I mentioned earlier, synthesis carried out at ambient pressure and the temperature will pose less load in our environment. Therefore, in our study, copper selenide narrow size powder are synthesized at room temperature and ambient pressure. Besides, the high temperature beta phase persistently appears as the major phase with the presence of low temperature alpha phase as minor phase in wet chemical synthesis. Therefore, we would like to clarify why beta phase is always present using solution methods instead of making pure alpha phase. And this pure alpha phase, you can directly synthesize using melting process without any presence of beta phase. And this is our reaction procedure, making tellurium doped copper selenide. It is a simple process, but need to be carried out with precaution at each step. First of all, copper selenide, copper chloride hydrates, selenium, tellurium powder are quantitatively and sequentially added into a reaction kettle containing DI water with stirring. Then sodium borohydrate is slowly added into the kettle and let the reaction proceed for 30 minutes at room temperature. The resulting powder are washed using DI water followed by drying in the vacuum oven for 5 hours and 80 degrees C. As I say, you have to be cautious because the powder are narrow size, so sometimes you will get the powder burned, but you get the powder from the dry oven. Since in the wet chemical synthesis, the ionized water and ethanol are often to wash away remaining chemicals in the routine practice, we reckon that the washing procedure might be associated with the transformation of alpha phase to beta phase. So in the process of our study, we discovered that pure alpha phase exists only in the synthesized powder without the presence of beta phase when the powders are taken out of the reaction beakers without further washing. You can see why I'm saying this from the X-ray diffraction pattern. In this plot, the middle indices in pink refer to the low temperature alpha phase. The green ones refer to high temperature beta phase. The purple ones refer to cuprous oxide. As you can see, the bottom X-ray diffraction pattern is for powder without washing. It is a pure alpha phase. The middle pattern is for powders wash with water, you can see quite a few amounts of alpha phase convert to beta phase, accompanied by the appearance of cuprous oxide. This result suggests that mobile copper ions on the unactivated surface size of copper selenide nanoparticles are highly reactive and react with the surrounding oxygen to form cuprous oxide. And if you look at the top pattern, this is for the powder washed with ethanol. Some alpha phase converted to beta phase, but there's no presence of cuprous oxide. And this suggests that copper ions are not capable of grabbing oxygen atom to form cuprous oxide from the ethanol environment. Okay. In order to better understand the formation mechanism of alpha copper selenide synthesized at room temperature, several experiments were carried out. We propose the following reaction mechanism for our room temperature synthesis of copper selenide. First of all, copper chloride dihydrate is dissolved in water and then form copper chloride hexahydrate, which is then reduced to elemental copper by sodium boron hydride. Meanwhile, elemental selenium is reduced to hydrogen selenide anion, which then becomes diselenide dianion by the reaction of oxygen, evident by the change of color. We'll get to that later. Diselenide dianion then disproportionate to nano-sized elemental selenium and selenium dianion. Then the nano-sized elemental copper and selenium react to form copper selenide. Therefore, the room temperature reaction is carried out between copper atoms and selenium atom. It's not like people said it is precipitation reaction. No, it's atom and atom reaction. So in our process, there's no need to do the synthesis using melting process of high energy consumption. Okay, the evidence of this proposed reaction mechanism is as follows. The actual diffraction pattern shows the formation of nano-sized elemental copper. You can see, the color change. We'll show you later. And the peak, the reaction here has a quite broad. It's quite broad. So this indicates the nano size. And also, if you put copper nanoparticle in the solution containing selenium powder and the sodium borohydride, the alpha phase form 5 minutes. In 5 minutes, you can see the low temperature phase. And this these photos shows the process of atom-atom reaction. From left, the copper chloride dihydrate is first dissolved in deionized water. You can see the color is quite blue, very beautifully blue. The copper nanoparticle forms immediately upon addition of sodium borohydride. You can see the second one from the left. After blue color disappears, the selenium element powder are added to the solution containing copper nanoparticle aggregates. Alpha copper selenide phase forms immediately with a red color appearing in the solution before the reaction completes. There's a little bit red color here, it's not very clear. Or you can see that from the top of the vial. And also you can, and for this photo B, this is what I tell you that I'm going to show you the evidence of diselenium dianion forms. Initially, if you put the selenium powder into a sodium borohydride with the cap tightened, then this is a clear solution. But when you open the cap, it becomes pink. Okay. So when the vial is sealed from air, the solution is clear. When the cap of the vial is open, the solution turns pale red, indicating that the hydrogen selenide anion is oxidized by oxygen to diselenide dianion, having red color. Okay, and also we compress the copper nanoparticle into a bar and they immerse in the solution containing diselenide dianion, and the dark copper selenide forms on the surface right away. And you can scratch off the surface and it becomes back the copper luster. Okay, for transport property characterization, we still need to use water to wash off the chloride and the boron-related compound from our copper selenide. Therefore, the beta phase seems to be inevitable existing in the synthesized material. Nevertheless, we discovered pure alpha phase can still be obtained by heating the powder at 650 degrees C for 6 hours in a mixture gas of 20% hydrogen and 80% nitrogen. These are the X-ray diffraction pattern of this series of materials. As you can see, for tellurium-doped copper selenide, the material is of pure alpha phase. However, the beta phase still exists in the material with the copper deficiency in Y is not equal to 0. If a copper deficiency, you still have the beta phase. And these are lattice constant for the tellurium-doped material. This result indicates the lattice expansion occurred just a little bit with a partial replacement of tellurium on the tellurium site in the lattice. And these are the chemical composition analytical result using ICP spectroscopy, indicating the composition of the material is quite close to the nominal ones. And this is our setup for high temperature transport property measurement up to 700K. In fact, they can go up to 800K, but if you crank it up to 800K, the crusty could be, broken in a few thermal cycles. So we only go up to 700K. Okay, and this is a commercial one. The other one is the this is the homemade. Okay, we write all the software, and this is a commercial one. I like mine better. This one has some problem. Okay. Okay. This is the view graph shows an electronic transport of the series of tellurium-doped copper selenide. It can already seen that introducing copper deficiency significantly reduce both the electrical resistivity and thermal power due to the enhanced Hall carriers by introducing copper defects. And these are consistent with the increased Hall carrier concentration. See the red line? The highest power factor of 11 microwatt per centimeter square at 818K is attained for a sample with X equal to 0.04, Y equal to 0.04 sample. And also you can see the phase transition occurred consistently in the electrical resistivity, thermal power. This is phase transition, okay? And also in thermal conductivity. You might wonder why there are no data between 500 and 700K. This is because the double spiral sensor used in our instrument, the hard disk thermal constant analyzer, is made of nickel, double spiral, and the nickel has a Curie temperature of 627K. So we will have a problem of TCR there. So the data is not reliable. So we do not make the measurement between 573 and 700K. Moreover, since thermal conductivity tends to decrease with the increasing temperature, we take the thermal conductivity, which is measured at the maximum temperature. We carry out an experiment in consideration of the costly hard disk sensor. As I told you, it's quite expensive. And the sensor easily deteriorates after a few thermal cycles going through high temperature. As you can see, all the thermal conductivity falls in the range of 1.0 and 2.1, below 600K, and within the range of 0.6 to 1.9, above 700K. Okay. We also analyzed the lattice thermal conductivity by using the single parabolic band model. This model is quite powerful in analyzing the transport parameters when you do systematic study of your materials through these formulas. Okay, so we use the formula to calculate. We use Weidmann Fresnel to calculate electronic thermal conductivity first. Okay, and then get the lattice thermal conductivity. Okay, so you can see here a ZT equal to 1.4 is a 10 at 920 K. For the sample X equal to 0, 104, and without copper deficiency. In view of the decreasing trend of thermal conductivity with increasing temperature, as you can see that the thermal conductivity decreases with the increasing temperature. So they are reported in the literature. So we can expect the ZT value is higher than 1.4 at the higher temperature. And these two plots show the reproducibility and stability of the sample. The sample after 1 year after the first measurement, we remeasure the same material and go through 2 thermal cycles, go up and down, okay? And we remeasure the same material and go through these 2 thermal cycles. As you can see, the remeasured data are quite close to the first measurement, which means this material is quite stable. Okay. Now this table compares the copper selenide fabricated by a combination of melting process and spark plasma sintering without fabrication method involving room temperature aqueous synthesis followed by heating at 650 degrees C for 6 hours under a flowing gas mixture of 20% hydrogen, 80% nitrogen, and then in vacuum at 650 degrees C for 6 hours. And you can see that our fabrication procedure is an energy efficient method. You can see that right here. See, our procedure only requires 8.5 kilowatt hour, and for the melting at 960 degrees C for 24 hours, that would take 46.4 kilowatt hour. And the other process, melting at 1000 degrees C for 24 hours, and then annealing at 427 degrees C for 72 hours, which is respectively require 18.6 and 38.6 kilo hours. So from this table, you can see our process is very energy efficient. Okay, as I said, calculating as I said, single parabolic band model is a powerful analytical tool when investigating thermoelectric transport. So we developed an algorithm called SPB-Cal, okay, to calculate the transport parameter within seconds. If you do it by hand, do your hand calculation, it would take hours to do that. So you can download the algorithm from the GitHub, okay? Okay, and this is how it looks like. You can calculate as many temperatures as you like. At the same time, as long as you enter the magnitude of the thermal power and the will carry concentration and the electrical resistivity. And this is how we got from this algorithm. You could have reduced permeate energy, and also you can get effective mass, okay? Again, you can get the Hall factor, and also can get the quality factor. Okay, this is a summary of the tellurium doped copper selenide series. Okay, we make the sample at the room temperature using sodium borohydride as reducing agent, and also we provide evidence of the alpha phase formed by the reaction between elemental copper and selenium atom at room temperature. And portion of the low temperature phase spontaneously transformed to high temperature phase during the washing procedure. And also we developed a procedure to fabricate single phase of alpha phase by cold pressing the washed and dry mixture followed by sintering at 650 degrees C for 6 hours in a mixture gas of hydrogen and nitrogen. such single phase of terrestrial copper selenide is fabricated using powder synthesized by chemical solution-based method, and we got ZT value greater than 1.4 at 920K. I think it's about the time, right? Yeah. So I think I will wrap up my talk, leaving the polymer film behind. And this is my group. And I just thank the financial support from most in Taiwan. And this is my group, well, the previous group. Most of them has left. Okay. Again, thank you. Thank you for your attention.
Okay. Thank you. Okay, thank you. Thank you very much, Professor Liu, for your very enchanting and illuminating lecture. But as I have found in the later part, there are some slides on the development of thermoelectric material based on the organic material, that is the organic semiconductors. So, but since you have just described the inorganic part, okay, we look forward to hear from you in future on the development of these material in the organic domain.
Okay, all right.
Okay, but I thank you so much for your such an illuminating and enchanting lecture where you have elaborated on how low energy consumption, that is energy efficient processes work for the preparation of various series of material and how the subsequent treatment tunes the properties of the material. But can I ask a question right now about the work which you have already done in organic material, that is in polymers. In polymers, the treatment which you are making for the inorganic series of material, those cannot be done in polymeric material or hybrid material or inorganic organic hybrid material. Okay, so then how do you think that this material, hybrid or the inorganic organic composite, the tuning of the ZT value can be done? Do you have anything, can you propose something in that line?
Well, in fact, this kind of process is, we are right now carrying out this kind of process. Okay, we're still investigating. We got one paper published. Well, this is the one. I'm sorry. Well, let me just. And this is a very simple process. You just do drop casting, okay? And then you can buy the PSS and you do the drop casting on the film, on the substrate, okay? And the key thing is that you have to remove some of the PSS because that is insulating. You can use a combination of the solvent, polar solvent, and also inorganic materials, okay? And you want to do the hybrid. You want to do the hybrid, like an inorganic organic hybrid. Right now, we are doing it, but not yet quite successful. Okay, so I cannot tell you more.
Okay. Okay, it's all right. Thank you so much, sir.
There are questions in the chat box.
Yes. There are some questions in the chat box. Professor Liu, can we have the question answer session now?
Okay, so yes. How could I see that box? I don't know how to do it.
Okay, I'll read out the questions for you, and I'll request you to address those. Okay. This first question is from our colleague, Dr. Shampad Mukherjee. How you choose the annealing temperature is 340 degrees for the samples. Have you done any thermal study like DTA or any other thing? The question is how the annealing temperature is chosen to be 340 degrees.
Okay. Okay, these are good questions. In fact, my students just do it by trial and error. We don't do any DTA because if you do a DTA, I don't think there's any phase transition or something else can be detected. You just do the trial and error to see what has the best power factor, and then he decided to use that temperature. Just try and error.
Okay, and the next question is, it is not a question, but it is just a request to share all the PPT of all the sessions. someone from Ashish Jadhav. He has requested to share the PPTs. And then another question from a researcher, Pinaki Mondal. He has, why resistivity reduced more when bismuth telluride, bismuth antimony telluride system was synthesized in 160 degrees centigrade instead of 140 degrees centigrade. If we synthesize at more higher temperature, then what will happen? Slide number 55.
Okay, let me show you the result first, okay? The question is here. This is the one, right? Why
Yes.
106? Well, in fact, you have okay, the synthesized. Oh, I forgot to tell you something more. 140 degrees C and 160 degrees C are synthesized by hydrothermal synthesis. But in fact, when you consolidate the sample, we have to use 340 degrees C to consolidate the sample for transport measurement. Okay, so both of them are centered at 340 degrees C. And the why the 600 degrees C has a lower resistivity than 140. In fact, 160 degrees C has a less tellurium in there. Okay, tellurium is kind of a impurity, then that would interfere with the conduction path. Okay. So is my answer?
Okay. Yeah. Got it. And the next question is, sir, in case of filtering carriers on the basis of their energy to increase the power factor, energy barriers are generated by introducing nanometric precipitates. Which parameter of those precipitates define what will be the height of the barrier, or up to which the energy carriers they can stop at the phase boundaries? This is another question from another research scholar.
Okay.
She's asking, yes.
In fact, this kind of energy barrier filter is also by
height of the energy.
Yeah,
yes.
It's only by well, what I can say is that researcher usually explain what they have, okay? But if you want to predict what kind of material can act as an energy barrier, I think this is very difficult, unless some theoretical people can do that, okay?
Okay.
So these are trial and error. But
yes.
the thing is that there's one basic principle. You can put nanoparticle embedded in the material, okay, to do this kind of a job, like filtering those carrier with low energy. That is the must, okay. But the problem is that if you add different nanoparticle, you could hinder the process of the conduction. So this is another thing, okay. So this is all by accident. It's not really people can predict what kind of material you can add it to the material to enhance the power factor.
Okay. Thank you, Professor Leo. Now, my colleague Minaj will just conclude the session. You please be with us for a few minutes.
Okay. All right. Thank you.
Thank you, Professor Liu, for your illuminating talk. Now we are going to conclude this session. Before that, I have a request to everyone. Please switch on your video. We'll have a photo session. One of our students will take a screenshot. Professor Liu, can you please stop your presentation?
Okay. All right. So I should leave out, right?
All the participants and the speaker and the chair, we all will.
Okay. I just stop the.
Take the photo together.
Okay.
Your screen is still showing, so.
I'm sorry. Just wait a minute.
Okay. No problem.
So is it done?
Participants, please switch on your video.
Yes, it is done.
It's done, right?
Yes.
Some of our PhD students, please take screenshot.
Minaj,
Yeah, please.
Professor Liu is not shown properly of the full face.
Yep. Professor Liu,
Alright.
can you, yeah.
Okay,
Please
okay,
give
now
us
it
the
is
answer.
fine. It's
Thank
fine.
you. Thank
Photo
you.
session.
It's great now.
Thank you
It's
so much.
great now. Okay, we are done, I guess.
Okay,
Yes.
thank
Thank
you.
you, everyone.
Thank you
Thank you to the
profusely.
participants, Professor Liu, and our
Yes.
chair, Professor Dipali Banerjee. So
Thank
Okay.
you.
we'll meet again at 3 p.m. with the talk of Professor Lorenzo Pavesi from Italy, Trento University, Italy, sharp at 3 p.m. Thank you.
Okay. Thank you.
Okay.
Thank you, Professor
Okay,
Leo.
bye then.
Thank you
Okay, thank
profusely.
you.
Okay.
Okay, bye.
Bye.
Yes, Lorenzo.
Hello.
Hello. Our plan is to start the program at 3 p.m.
Yes.
So let's wait for a few minutes.
Yes.
Let's wait for some more people to join. We're expecting some more people to join here in the Google. Yes, Lorenzo.
Hello.
So we'll start at 3 p.m. Exactly. Our plan is to
I'm
start
ready.
the program at 3
When
p.m.
you want, yes, we
So
can
let's
start.
wait for
I'm
a
here
few
at
minutes.
your, yes, disposition.
Let's wait for some more people to join. We're expecting some more people to join here in the Google. Yes, Lorenzo.
Hello.
So we'll start at 3 p.m. Exactly. Our plan is to
I'm
start
ready.
the program at 3
when
p.m.
you want, yes, we
So
can
let's
start.
wait for
I'm
a
here
few
at
minutes.
your, yes, disposition.
Let's wait for some more people to join. We're expecting some more people to join here in the Google. Yes, Lorenzo.
Hello.
So we'll start at 3 p.m. Exactly. Our plan is to
I'm
start
ready.
the program at 3
when
p.m.
you want, yes, we
So
can
let's
start.
wait for
I'm
a
here
few
at
minutes.
your, yes, disposition.
Let's wait for some more people to join. We're expecting some more people to join here in the Google. Yes, Lorenzo.
Hello.
So we'll start at 3 p.m. Exactly. Our plan is to
I'm
start
ready.
the program at 3
when
p.m.
you want, yes, we
So
can
let's
start.
wait for
I'm
a
here
few
at
minutes.
your, yes, disposition.
Let's wait for some more people to join. We're expecting some more people to join here in the Google. Yes, Lorenzo.
Hello.
So we'll start at 3 p.m. Exactly. Our plan is to
I'm
start the
ready.
program at 3
when
p.m.
you want, yes, we
So
can
let's
start.
wait for
I'm
a
here
few
at
minutes.
your, yes, disposition.
Let's wait for some more people to join. We're expecting some more people to join here in the Google. Yes, Lorenzo.
Hello.
So we'll start at 3 p.m. Exactly. Our plan is to
I'm
start
ready.
the program at 3
when
p.m.
you want, yes, we
So
can
let's
start.
wait for
I'm
a
here
few
at
minutes.
your, yes, disposition.
Let's wait for some more people to join. We're expecting some more people to join here in the Google. Yes, Lorenzo.
Hello.
So we'll start at 3 p.m. Exactly. Our plan is to
I'm
start
ready.
the program at 3
when
p.m.
you want, yes, we
So
can
let's
start.
wait for
I'm
a
here
few
at
minutes.
your, yes, disposition.
Let's wait for some more people to join. We're expecting some more people to join here in the Google. Yes, Lorenzo.
Hello.
So we'll start at 3 p.m. Exactly. Our plan is to
I'm
start
ready.
the program at 3
when
p.m.
you want, yes, we
So
can
let's
start.
wait for. Okay, it's 3 p.m. now. So good afternoon to everyone. We are on the third and the final day of the international webinar on advances in electronic, optoelectronic, photonic materials and devices. We started this day today in the morning, a very illuminating talk by Professor Chia Jai Liu from Changhua University, 3 p.m. now, Taiwan. So good afternoon to the everyone. Talk was on thermoelectric. We are on the third and the final day of now, we are going to start the afternoon session. Actually, the seventh technical session, photonic webinar and devices with Professor Lorenzo Pavesi. We started this day today. Lorenzo is from University of illuminating talk by Italy. Professor Jai will talk on quantum silicon photonics. Liu. We are thankful to Professor Pavesi for accepting our invitation and getting some time from his extremely busy schedule to enlighten us with his webinar. In fact, Lorenzo came to our institute physically many times. Probably for the first time he came in the year 2004, as far as I remember. And the latest visit was in 2019 December to the IIEST PhD held in December Center, Kolkata. Now, this session will be chaired by Dr. Anirban Mitra, Associate Professor in the Department of Physics, IISc Roorkee. Dr. Anirban Mitra got his BSc, MSc and MSc degrees from Jadavpur University and then PhD degree from IIT Kanpur. After that, he was associated with few postdoctoral positions in Institute of Laser Engineering, Osaka University, held in December Center, Kolkata. Trinity College, Dublin, and Dublin by University of Ireland. After returning back to India in 2008, he joined the Department of Physics. Since then, he is carrying out research in the area of optical properties of plasmonic materials and wide bandgap semiconductors. He has published around 50 research papers in peer-reviewed journals. He has guided 5 PhD theses and several MTech and MSc projects. Now I invite Dr. Mitra to chair the session. Just before that, I have an announcement that we are hosting this webinar through Google Meet, as well as this Google Meet is being streamed through YouTube live streaming of our institute, IIEST Live. So the participants, if you have any query, you can put your queries and questions in the chat box. And the participants who are viewing YouTube streaming, you can also put your questions in live comment box. Our representatives will take your questions and put them in the chat box of Google Meet, and we'll convey the questions to the speaker through the chair of the session. Dr. Mitra, please take the chair.
Okay, thank you, Professor Minaj. So now it is my pleasure to welcome Professor Lorenzo Pavesi to this international webinar on advances in electronics, optoelectronics, photonic materials and devices. Professor Lorenzo Pavesi is a professor at the Department of Experimental Physics at University of Trento, Italy. He received his PhD in physics in 1990 from the École Polytechnique Federal of Lausanne of Switzerland, and he founded basically he has started the research activity in semiconductor optoelectronics at the University of Trento, and then several other laboratories of photonics, growth and advanced treatments of materials. His research activity mainly concerned with the study of optical properties of semiconductor, the properties of the group 3 and group 5 semiconductors grown on Nobel index surfaces, hydrogen in semiconductors, impurity diffusion in gallium arsenide, disorder in superlattices and photonic crystals. During the last few years, he concentrated on the silicon-based optoelectronics, where he looks for the convergence of between the photonics and the electronics by using silicon nanostructures. And he is interested in active photonics devices which can be integrated in silicon by using classical waveguides or novel waveguides, such as those based on dynamical photonic crystals. His interest encompasses also optical sensors and biosensors. In silicon photonics, he is one of the worldwide recognized experts. He is an author or co-author of more than 250 papers, author of several reviews, editor of 10 books, author of 2 books, and holds 5 patents. He was in the editorial board of Journal of Nanoscience and Nanotechnologies. He was also in the directive council of Lens of Florence, and also in the board of delegates of EMRS. So now I welcome and request Professor Lorenzo Pavesi to start his lecture. Okay. Okay, please, Professor Pavisi.
Okay, thank you for the introduction, and thank you, Professor Hussain, for inviting me to join this seminar. And today, what I want to talk to you is about our recent work on quantum silicon photonics. And before entering into the detail of the topic, I would like to acknowledge my previous visit here in Shibpur, which was actually in December 2019. And I really enjoyed the visit, and here you see me sitting together with the director of the institute as well as with Professor Hussain. And maybe a few of the people in the audience can recognize themselves in this photograph. And that was really a nice visit where I really appreciate the facilities and the institute. So let me start talking about where I'm coming from. So I'm coming from Trento, Italy. And Trento is in the north part of Italy, between mountains. And here you see a photo of the downtown Trento. So my topic will be about photonics. And maybe before going to the detail of the topic, I would like to say what I do mean by photonics. So actually, as you know, photonics is the science of light. And typically you do photonics by using optical components, big lasers, optical table, and so on and so forth. For me, photonics is different. So for me, photonics is something that happens at the chip level. And so what we are working with is integrated photonics. So the World Photonics Lab for us is a very small chip where all the different photonics components are integrated. The reason why we go to photonic integrated circuit is because we can have much more efficient devices with respect to what we usually have on a tabletop. And the reason of the increase of the efficiency of the device is that the alignment of the optical path is stable since it's given by the circuit, and then therefore you get less noise as well as less losses. On the other side, the use of photonic integrated circuits allow you to reduce significantly the dimension of the devices, the cost of the device, as well as the possibility to merge photonics with other technologies. And this led me to introduce the kind of photonic integrated circuit I'm typically work with, and these are realized by using silicon. And therefore, the technology is called silicon photonics. By silicon photonic, what I mean is photonic devices that are fabricated by using silicon and standard silicon processing. And this means that we can leverage on the microelectronic industry in order to get volume fabrication and therefore cost reduction, increase in the market size, as well as increase in the performance. Moreover, if you use silicon to implement a photonic circuit, so you have at the very same time also the possibility to merge on the same circuit photonics with electronics. So that therefore you have a large space for improvement. And in silicon photonics, what we did was to follow the same paradigm to success as with microelectronics, which means we try to increase the level of integration. So a few years ago, we were working at the SIP level, while nowadays we are really working with very integrated photonics as well as electronic circuits. So in the microelectronics, people is trying to look at what is going to be after when the limit of the Moore's law will be reached. So here is a cartoon where you see as a function of the year, so the increase of the performance and the reduction of the power in microelectronics components. And what did this cartoon show you is the fact that now, so we are approaching the limit of the Moore's law. And the solution that the new approaches that are indicated are essentially towards two different directions. So the first one is artificial intelligence, meaning the use of devices that get inspiration on how the brain is working. So those kind of computing is called neuromorphic computing. And the second direction is towards the use of quantum physics to enable faster and more powerful computation. So these are the two directions where we are working on in my lab. So one is neuromorphic computing, which means new computing scheme based on classical physics, but getting inspiration by the brain. And I will not talk about those devices and those results that we are getting, but if you are interested, you can go and have a look to this web page. On the other side, we are also working on quantum, which means that new computing schemes that are based on quantum physics. And in this field, so there is a lot of different possibilities. There are a lot of different possibilities to implement quantum physics for getting a quantum computer. And actually, economists a few weeks ago showed this cartoon where it stated that the quantum computing race is started, which means that there are different platforms on which you can implement the quantum computers. So you can use superconductors, you can use atoms, cold atoms or ions, and as well as you can use photons. And we are here on this car. We are trying to use photons in order to implement quantum physics and get novel devices. So this is the topic of quantum silicon photonics. And this is going to be the topic of my presentation of today. So, at the beginning of last century, the first quantum revolution started. So the quantum mechanics was demonstrated, and based on the demonstration of quantum physics, many different breakthrough devices has been invented. So you know the transistor, the integrated circuit, the laser, microprocessor, and the technology that is behind nowadays society. Then at the beginning of this century, in 2000, people start to think to the second quantum revolution. So the first one was the one that carried on. Here you see the map of the world, and you see that all the different countries are actually sustaining very aggressive programs in quantum technologies. For example, India is here, so $1 billion. So what is the second quantum revolution? What are the principles at the base of the second quantum evolution? So here the idea is to develop a technology that is essentially based on the fundamental properties of the quantum system. So in the second quantum revolution, not only we explain how matter is working, but we also try to use in devices the fundamental principle of quantum mechanics. And these fundamental principles are the fact that the nature is granular, so the fact that we want to use in technology the quantization of matter, meaning that we want to work with single particle, single photon, single electron, single magnetic flux, single. The second idea that we want to exploit is the fact that the quantum mechanics predict that particles can be in a superposition of two states. So you know the example of the Schrödinger cat, where you have that the cat within the box is in a superposition of an alive cat as well as a dead cat. And this is a superposition of two states. So at the same time, the cat within the box is alive or dead. It's not alive, within the box, the cat is alive and dead. It's not alive or dead. So it's in a superposition of being alive and dead. And this allows you to introduce the qubit, which differs from standard bits, because standard bits can be 1 or 0. Any other value is an error. So if you have a bit that is equal to 0.5, you have to reject the bit in digital computation because this is an error. While in quantum computation, you use qubits, where your bit, qubit, is in a superposition of 1, there is an error in this slide, is in a superposition of 1 and 0. So you are working with a state that can be any value between 1 and 0. And this is the principle of superposition that we want to use in quantum technology. Then the actual result of the computation you only get when you measure. So when you collapse the wave function on a well-defined state. And then the last and most important properties that we are exploiting in quantum technologies nowadays is the entanglement. So this is strange state of correlation between two different particles. So let me show you a few examples of technologies that are based on those properties I have shown you. So let me use and demonstrate the first device that is based on the single particle nature of light. So it's based on single photons. And here the problem is related to security. And the idea is that you want to send an information from a sender to a receiver in such a way that a potential attacker cannot guess the information that you are sending. And so what you do, essentially, you use keys in order to cipher your data. And so this is the use of quantum mechanics to enable new schemes for cryptography. And so essentially the idea here is to produce keys that cannot be guessed by an eavesdropper. And to produce these keys, so you use random numbers. And so what we want to do is that we want to generate random numbers that are certified by the quantum nature of physics. And the reason why we want to quantify, to use the quantum physics to produce this random number is because the randomness is intrinsic in quantum physics. So let's do an example. So in order to produce this random number by using quantum physics, so we take one photon, we let the photon to pass through a beam splitter. And therefore, we know that the photon at the beam splitter can pass through or can be reflected by. And then by using single photon detectors, so we can detect whether the photon went through or was reflected. And according to quantum physics, so we have that the outcome of the measurements will be 50% of the time the photon will go here, and 50% of the time the photon will go there. From a classical point of view, so you can think that this experiment is like tossing a coin. However, there is a very fundamental difference between this simple experiment and tossing a coin. The reason is because that when you toss a coin, so then you do not know whether you end up with a head or a cross. And the reason is simply because you think that this is a real random outcome. However, if you know exactly what is happening, so you know all the initial conditions, classical mechanics tell you that you predict with certitude the outcome of your experiment. And so the reason why we don't know exactly the result of tossing a coin is simply due to the fact that we do not know exactly how the initial conditions are. And so what we do is that we assume a statistical model in order to describe the experiment. In quantum mechanics, we do not assume any statistical model. So in quantum mechanics, so we know that we are able to describe exactly all the conditions of the experiment. However, since quantum mechanics is intrinsically probabilistic, unless you do a measurement, you don't know whether the photon is here or is there. Because actually, the result of the transmission of the photon by this beam splitter is a superposition of states between one photon on this arc and one photon on that arc. And so what the difference between the quantum and the classical random number generator is the fact that in quantum you cannot guess the result of the measurement, while in a classical random number generator you can by 100% tell the result of the measurement, provided you know exactly all the starting conditions. And so this is the reason why you use quantum physics to produce this random number. And the idea of our system, of our device, is very simple. So we use spontaneous emission. So this is a process by which you have an electron in a conduction band in a LED, and you never know when actually this electron recombines with a hole and the photon is emitted. And so this spontaneous emission, which is intrinsically a probabilistic phenomena, provide us the entropy, provide us the randomness in our random number generator. So what we did is essentially we calculate the conditional probability that provide that the photon is emitted in a large interval. So we consider the fact that the probability that provided photon is emitted in an interval capital T, we look at the exact subinterval where the emission occurs. So we are sure that the photon has been emitted, but we don't know where exactly in the different subinterval of capital T the photon is emitted. And so when the photon is emitted is our random number. So what we did is that if the photon is emitted in the first subinterval, so we assign a symbol 1. If the photon is emitted in the second subinterval, we assign a symbol 2, and so on and so forth. And so in this way, by measuring when the photon is emitted, so we can produce a stream of random numbers. And so the experiment is very simple. So we have a source of photons, a detector of single photons, an electronics to do the timing, and then the result is our sequence of random numbers. So this is the statistical test that the binary stream has been submitted to, and all the tests are passed. So that means that actually the numbers that have been produced are actually random. And what is even more important is the device and the random number extraction method is robust from external attack, meaning that an external attacker, by changing the ambient condition, by changing the current in the LED, by changing the experimental parameter, cannot influence the production of the random numbers. Here you see an example. So this is the electroluminescence, so the number of photons per second produced by our LEDs as a function of time when we change the temperature of the ambient. And you see that the electroluminescence is strongly dependent on the temperature of the LEDs. So if you increase the temperature of the LEDs, So the electroluminescence, also the photon flux, is significantly reduced. However, if now you count the probability to get 0 and 1, you see that this probability is always 0.5. So the randomness is not affected by change in the ambient temperature. So the random number generator is extremely robust with respect to external attack. And so the first experiment had been done by using an LED and a single photon detector. Then we have made everything on two different photonic integrated circuits. We phase one to the other. Then we have bonded the the source to the single photon detector. And finally, we have integrated everything within a very small chip. And so this is the evolution of the device. And then this kind of quantum random number generator integrated in a small chip is unfortunately not ours, but is now integrated within a smartphone. And actually Samsung, a few months ago, so this was the middle of last year, so May 2020, announced the possibility to buy a smartphone which has integrated in a quantum random number generator. So this means that the second revolution has produced devices that are now available on the market. So I will show you another example of random number generator that is now based on entanglement. And the use of an entanglement is because we want to certify the randomness that we have produced. And here is the idea of the entanglement. So you take two particles, different particles, and then you use this in non-local correlation between the two particles. So this is the usual approach of entanglement. However, and then you can use this entanglement to produce quantum random number generator. However, in our case, so we are exploiting a different kind of entanglement. An entanglement that is not between different particles, but is an entanglement between 2 degrees of freedom of the same particle. So what we are entangling here is the quantum state of the particle. And so in our approach, so I should also thank the people that collaborate in this work. So in our approach, what we are entangled is the 2 internal degrees of freedom of one photon. And so the state that we are produced is a superposition between a photon that has a momentum and a polarization with the same photon with another momentum and another polarization. And so the momentum for us is a different path, a different direction through which the photon is propagating, and the polarization are two well-specified polarization state of the photon, either vertical or horizontal. And so to generate this entangled state of the single photon, so we use a very simple setup. So we get a photon, we fix a direction and the polarization state of the photon. So this is the input state of our photon, which is going in the x direction, we call zero direction, the zero state for that direction, and has a vertical polarization. Then through a beam splitter, we produce a superposition of a photon that is moving in the y direction, so it is characterized by a state 1 for the momentum, with a photon that has went through the beam splitter, so it's still moving in the x direction. So here we have a superposition between a photon in the vertical polarization state that is moving in this direction and in that direction. Then we use a halfway plate by which we rotate the polarization state of the photon in this direction. So at the end here, we get an overlap, a superposition between a photon state that has an horizontal polarization and is moving in this direction, with a photon that has a vertical polarization and is moving in that direction. And so this is an entangled state produced by a controlling 2 degrees of freedom of the same photon. And this is what we are using in order to produce quantum random number. So this is a single particle entangled state. Once we have the photon, then we have to demonstrate that indeed we have an entangled state. And in order to do that, we perform a Bell inequality measurement. So a Bell inequality measurement is a witness of entanglement. So according to this Bell inequality, if classic physics is ruling the experiment, then the product of the measurements we are going to perform should be equal or less than 2. If you find a result that is larger than 2, so then the state that you are measuring is not describable by classical physics, therefore should be a quantum entangled state. And so in order to do that, what you have to do is that you have to project your entangled state over a basis, and you have to change and you perform a scan in the different momentum and polarization states. And in order to scan in the momentum state, we use a Mach-Zehnder interferometer. So this Mach-Zehnder interferometer here. And so by controlling the relative phase between the photons that is traveling in this arm and the photon that is traveling in this other arm, so we can change the momentum states. And then by using 2 half-wave plates that we use to rotate, so we can change the polarization states. And then at the end, so we are going to detect. Here we have a polarization splitter. So the photons that are traveling along this path here and move through this polarization splitter are in the 1H state. So momentum 1, polarization horizontal. And then we detect them. The photons that are instead reflected by this polarization splitter will have momentum 1 and polarization vertical. And then here we have the very same detection line. However, in this case, the photon is traveling in the x direction. So we have a momentum 0. And in this case, polarization B, and in this case, polarization P. And so then, by counting the different detection events, so we can build up the parameter that is the S parameter, where we have the sum of this function. And if S is smaller than 2, so then the Bell inequality is not violated. If S is larger than 2, so then the Bell inequality is violated. And here what you see is that when you use a laser to produce the photons that we are going to measure, so you see that there is an interval of the input of the input state. So there is an interval where the Bell inequality is violated. So here, by putting the state in this condition, so we know that the 2 degrees of freedoms are quantum correlated. So we have an entangled state. What is also nice here is the fact that we do see violation of the Bell inequality not only with the laser, but also with an LED. And also, what you see here is that we can produce the photons by using an halogen lamp. So that means that in order to perform the experiment, you can do an experiment by using a very simple, cheap, low power consumption LED instead of a high power laser to induce a parametric process in a non-linear crystal that yields you the 2 particle entangled state. And so this is a real change in the way we produce entangled states. Because instead of having massive, costly, high power consumption laser, so here we can use a very simple lamp, a very simple LED, a very simple experimental setup. So this is the source of entangled state. And then what we do is that we use the source of entangled state to produce random number. And the way we produce the random number is very simple. So we tag the kind of the specific detector that has clicked in the specific time being. And so we introduce one photon, we generate the entangled state, then we rotate in the momentum and degree of freedom space, and then we look at we let the entangled state wave function collapse on a very well-defined state, and we look at which one of the different detectors has clicked. And so if the detector which clicked is the detector that is measuring a photon with a momentum 0 and a polarization vertical, so then we store as random number the symbol 0, 0. If instead the clicking is 0H is from the detector that is measuring 0H state, so we get 0, 1, 1V, 1, 0, and so on and so forth. And since we cannot predict which one of the 4 detectors is clicking, so in this way, so we are producing a sequence of random numbers. And then we use the Bell's theorem to certify the randomness of our numbers. And by using and analyzing the experiment that we are performing, so we can end up with different kind of a minimum entropy generated according to the quantum phenomenon. So if we assume to not know anything in our experimental setup, which means that the system is semi-device independent. So here, the only thing that we know is the photodetector. So we describe the photodetector, but all the rest of the system is unknown. And so this is the situation where we are in the maximum security level, meaning that an external eavesdropper can modify the experimental setup, and even though the experimental setup is controlled externally by the eavesdropper, we can extract random numbers because the knowledge of the band inequality, because of the knowledge of the quantum physics. So in this case, so we get the percentage of mean entropy of 2.4%, which means that among all the numbers that we are receiving from the setup, the 2% are certified of being random. This means that in this case, we get a throughput, so a random bit generation rate of 4 kilohertz. But then, if we start to increase the knowledge, so the trust on the setup that we are using, meaning the trust means that we assume, we trust what we have in our hand, so we are able to describe exactly all the different components in our experimental setup. No external attacker has modified the experimental setup. We can increase the percentage of mean entropy. In this case, it means that of all the random numbers that we are collecting, the 30% are certified to be random by the quantum process we are considering. And this will increase the throughput from 4% to 52%, for 4 kilohertz to 50 kilohertz. And this is 50 kilohertz of certified random number. So where are we now? So we did this experiment on a tabletop, and then we are testing an integrated circuit that is able to undo and produce our random number. And in this way, so we are squeezing down the surface of the setup from roughly 1 square meter to only 1 square centimeter. So this is going to be used also within a collaboration we have with India in quantum physics within the India Trento Project for Advanced Research, and we are collaborating with esteemed colleagues here. here in India. Here, the second example I want to show you is another example that uses the entanglement for producing sources for quantum computing. So the idea we have, which is summarized in this review paper, is to use the concept of heralding in order to produce single photons. And let me thanks the people, the collaborator in this work, Stefano, Matteo, and Sara, and show you the application of this single photon heralded source for mid-infrared. So here the idea is to produce mid-infrared single photons to be used for gas spectroscopy. So the question is, how can we generate a single photon? So we can use an attenuated coherent source. So you take a laser, you attenuate the laser at the level that the number of photons, so the photon flux, is significantly reduced. And so you can assume to have a single photon. However, if you do the photon statistics, you realize that most of the photon states do not have photons. And so this is not a single photon source, because a single photon source is a source where you have all, in each state, you have one photon. Here, what you end up is many states with zero photons. And so the idea here is to get the concept of rounding. So the concept of rounding is very simple. So you take two photons that are correlated in time, and then you measure one of the two photons, and the measurements of this photon herald the presence of the other photon. And so in this way, in the photon statistic, you completely remove the zero photon state. And the reason why you remove the zero photon state is because you know that you have, since you start from correlated in time photons, you know that you have the photon in that state. And so this is going to be reduce the zero photon state, increase therefore the one photon state, and you get something that is very similar to a single photon source. The only problem with this kind of principle, that is the heralding principle, is the fact that the source is still probabilistic. You don't know when the correlated photons are emitted. So how can we actually produce this single photon source? So we use a nonlinear optical phenomena that is four-way mixing, where you pump a waveguide, and then spontaneously, if the pump level is large enough, spontaneously the two photons of the pump emit, decay into a pair of photons that are called the signal photon and the angular photon, that satisfy the energy conversion rules, by which the frequency, the sum of frequency of the two pump photons is equal to the sum of the frequency of the signal and the angular photon, as well as the phase matching condition. And so what happens here is the fact that the two photons, so the signal and the angular photon, are correlated in time, because they are generated at the very same time. And so this is the kind of source that we want to use, because in this way, so we have a pair of photons that are correlated in time. And so we can herald one by measuring the second. And this process here shows you the reason why I was saying that this source is a probabilistic source, because we cannot know when the two time photons generate the signal and the angular photon. Actually, so we are achieving the phase matching condition by using the so-called intermodal four-way mixing, meaning that we are using different waveguide modes to fulfill the momentum conservation. And the fact that we use different modes allows us to get a large separation between the frequency of the angular and the frequency of the signal. So the physics is explained in this paper. I have no time to go on. So this is the integrated circuit that realize this integrated four-wave mixing, by which we have a multimodal waveguide, and then we generate by using a specific circuit a pan photon in a fundamental optical waveguide mode, and another pan photon in the first excited mode of the waveguide. So this is T0 and this is T1 mode. And then we have a multimodal waveguide by which we generate a signal photon, a signal photon and a Heidler, sorry, the vice versa. So a Heidler photon and a signal photon, and then we collect the Heidler photon, we measure the Heidler photon, and then we, by doing these measurements, so we around the presence of the signal. And by using this technique of intermodal four-way mixing, so we are able to generate the Heidler in the mid-infrared at 2 micron, while the signal is generated at 1.3 micron. And then we need to prove that this Heidler photon is indeed a single photon. And in order to prove that, so we perform an Anderson experiment by which we take the photon and then we let the photon to go through a beam splitter. And then we detect either by this single photon detector or that photon detector. And say if here we have a single photon, we cannot have that at the same time this detector click and this detector click. And so by doing 3 photon coincidence measurements, where we measure the heralding photon and we measure the heralded photon either by this one or by that one. So by doing 3 photon coincidence measurements, we can prove that we have a single photon generated by our source. And so this is the outcome of the 3 photon coincidence measurements. And what you see is that if you delay the measurements between the 2 photodetectors, so you measure a certain level of coincidence. But when you do not delay the measurements of the 3 photodetectors, so you see that your coincidence measurements drop to almost 0. So that means that you cannot measure at the same time by this detector and that detector, which means that you only have 1 photon here, and so the photon can go there or can go there. So you never can have a coincidence measurements between those 2 photons. And so this showed that indeed, so we were able to produce this this heralded single photon detector. And this actually is the first on-chip source of mid-infrared heralded single photons that have been demonstrated. And what is even more interesting is the fact that now, if we change the wavelength of the pan photons, so we can change the wavelength of the signal photon. So that means that we can do spectroscopy. And indeed, if you look at the wavelength, the tuning wavelength of your single photon in the mid-infrared, you see that this tuning wavelength overlaps with the absorption spectrum of carbon dioxide. So those are experiments that we are doing right now. This kind of source can also be used for demonstrating on-chip another concept that has been pioneered by Anton Zillinger a few years ago. And the concept is the concept of the undetected photon event. So here the idea is extremely clever. So what you have here is 2 sources of entangled photons. So you have the first source, the second source. And then here you have the Heidler and the signal. And from the second source, you get the Heidler and the signal as well. But then what you do is the following. So you look at the quantum interference between the photons, the Heidler photon of the first source and the Heidler photon of the second source. And if you do properly the math, you see that the interference between those 2 photons is a affected by the interaction of the signal photon that you are not measuring with an object. And so that means that you can measure the properties of the object by the interaction of one photon while you are not looking at that photon that has interacted with the object. This means that you can do imaging by not detecting the photon that has interacted with your object. You are doing imaging by using the intrinsic properties of the quantum mechanics. And so this is a technique that we are implementing on chip, and is a technique that is called imaging with undetected photons. But let me go and move to the conclusion by showing that by using this source, it's also possible to generate extremely pure single photon states. And so the idea we had was to produce near ideal spontaneous photons by using this source. So a single photon is a single photon. An entangled photon is entangled photon. So the single photon is independent from the other photon. The entangled photons show correlation between the two photons. So what we want to do is that we want to break the entanglement in order to get factorizable state, so that we have that the photon that is produced in our era, the source, is very similar to a single photon state. And so to break the entanglement, what you have to do is that you have to remove correlation between the two photon states. And to reduce the correlation between the two photon states, either you filter out the signal and either photon, and in this way you get the uncorrelated state. So you see, those are two states that are uncorrelated, because if I do change the signal wavelength, I'm not affecting the Idler wavelength, or vice versa. Okay, if I'm changing, for example, here the Idler wavelength, the signal wavelength, the Idler wavelength is not affected. So this is completely uncorrelated. And you say that you have uncorrelated photon when the purity of your state is equal to 1. And we use the intermodal spontaneous Fourier remixing that is characterized by a very discrete generation band in order to demonstrate the purity of our source. And so this is the device. So the result is reported in Nature for Communication, result from a collaboration within our university and the Bristol University. So this is the device, and this is the outcome. So this is the photon density of states that show you that indeed you have very uncorrelated, very high purity photons. What is even more interesting is the fact that now, if you integrate two sources of photon on the very same chip, so you get that you cannot distinguish between those two photons. So that means that you get a single photon that has a very high level of indistinguishability. And to demonstrate the indistinguishability, so what we did was to perform quantum interference between those two photons. And we get a very high visibility in the interference spectrum. So, conclusion, why do we need the single photons? Because the photonic platforms can enable quantum computation. And here is the report of the result of in December by a Chinese group that have shown a significant quantum advantage by using a photon platform. And actually, so what they did was a calculation that takes only 3.5 minutes of a problem that would have taken an estimated 2.5 billion years on a classical supercomputer. So this is the kind of advantage that you can get by using quantum photonics. The quantum photonics field is very hot. Here is a company in California that has raised $215 million to produce the first silicon photonics quantum computer. So, take-home message, silicon photonics is a mature technology that allow you to demonstrate devices that are now moving to the market. Quantum technology can benefit from the dense integration, scalability, robustness, and low losses of silicon photonics circuits. Finally, a lot of new physics and new devices are still to be discovered by using quantum photonics. So the field is very hot and requires bright students. So I want to acknowledge people in my group. If you are interested, you have to go to the webpage of the group and you see what we are doing. Those are specifically the people who are working in quantum photonics: Stefano Azzini, Enrico Moser, Stefano Signorini, Massimo Borghi, Nicolò Leone, Matteo Sanna, Riccardo Trenti, e Davide Peretti. I would like to acknowledge the funding for the quantum science activity in my group, European Commission, the Trento, India Trento project of advanced research, and the initiative Quantum Science and Technology in Trento. Here are a few references, and I'm looking for PhD students that are able to take the big challenge I've shown you, both on quantum photonic as well as in photonic neural networks. So if you are interested, so please write me an email and we can see. Okay, thank you very much for the attention, and I'm done.
Okay, thank you, Professor Pavesi, for such a nice talk and enlighten us with your research work consisting of the single photon generation and the quantum computation using the silicon photonics. Now the session is open for question and answer. So I don't know that questions will come through the chat box or they can.
Yes, there are questions in the chat box already, so you can read it out. Dr. Mitro, it's there in the chat box. There are two.
Where is that? The right side, no? Okay.
Yes, right top corner.
Right. Yes. So there is, I think, 3 questions. Okay, one by one. One is from
two questions, I guess.
Huh?
2 questions. The first
two. Here 2 persons. So one is I think Dr. Sayari Basu. So what he asked is that emitted photons generally have lifetime of the order of nanosecond. If there will be any problem in detecting them with this SPAD detector, that is a single photon detector.
Very good question. So thank you. Correct. So clearly the nanosecond lifetime refers to 3-5 semiconductor. Here we are in silicon, so the lifetime are much longer than a few nanoseconds. But this is correct, and this is actually the reason why the time response of the photodetector, by which the generation rate is only in the order of a few megabits per second. Because, as you correctly point out, if you are using SPAD photodetector, you have the dead time of the photodetector. So once the SPAD has counted one photon, so then it takes some time to recover and be ready to detect the next one. Actually, so there are a solution to this problem is to use superconducting nanowires, and they have a much faster response time, as well as a immensely huge efficiency. So with silicon nanowires, you can go up to an efficiency of 95–99%, while with a SPAD photodetector, the photodetection efficiency can be in the order of 20 or 30%. And this clearly changed completely the generation rate in terms of ability to detect the photon. However, the problem with the silicon nanowires, with the superconducting nanowires is the fact that you have to work at cryogenic temperatures. So typically they work at 2 Kelvin, which is very low temperature and makes your setup extremely complicated and expensive. Hope to have answered the question.
Okay, thank you. So then there is another question. There is also another question. I think it is same, no, as it is slow in detection. So there is another question by Dr. Subhajit Rai Chaudhuri. is there any particular choice of beam splitter having particular reflection and transmission probabilities to generate random bits, or any combination of them will do the work?
This is also a very good question. So, actually what happens is the following. So let me show this table here. So what is happening here? So here it is happening that when we consider semi-device independent, so we say we don't know anything about the properties of the beam splitters. So they can have balanced reflection and transmission, polarization dependent for reflection and transmission. So someone can change the ratio between the transmitted and reflected beam. Then we end up with a minimum entropy of 2%. But then if we do trust, and so we describe exactly the beam splitter, knowing how much light is reflected, knowing how much light is transmitted, knowing what is the polarization ratio of the light that is transmitted and reflected, so knowing exactly the properties of the actual beam splitter that we are using in our setup, so then we can increase the minimum generated minimum entropy. But this means that in this case, so we need to trust fully the experimental setup that we are using. And so this makes the difference between the semi-device independent, untrusted system with respect to the fully trusted and device-dependent scenario. And then the question is, can you generate the single particle entangled state by using other setup than the one that you are showing? Yes, the answer is yes. And indeed, here in the integrated photonic circuit, here we are using a different concept. However, I cannot tell you the specific concept now because we have a patent that is going to be granted. Finish the answer.
Okay, I think there is no other question. So, Professor, thank you very much. And I have one question regarding this silicon. In that silicon waveguide, you are showing some 4-wave mixing. So generally in 4-wave mixing, we use nonlinear crystals. But is it how it is possible in that silicon to, yeah, this slides only?
So this what we are using is the fact that silicon has a very high chi-3 coefficient. In addition, for example, with respect to optical fiber, what you have in, so the chi-3 for silicon is 2 orders of magnitude larger than the chi-3 for in optical fiber. And then what you also have is the fact that the power density is going to be much higher than in optical fiber because of the small modal size that we have in silicon photonics. So the typical waveguide for telecom wavelength, single mode waveguide for telecom wavelength in silicon photonics has a sub-micron cross section, meaning 500 nanometer wide and 220 nanometer thick. In this case, so we have slightly larger waveguides because we are interested to move to the mid-infrared. The typical size of the waveguide that we are using here, so they are multimodal waveguide, is 2 micron in width and 500 nanometer in height.
Okay. Okay, thank you.
Here you can see the efficiency of the generation, which is a few hundred dBm, so very weak.
Oh.
This is a spontaneous process, so the generation probability is 50 dB.
Okay, so if there is no other question, then maybe we can close this.
Dr. Mitra, before closing the session, let's have a photo session. May I request everyone to switch on their videos. We want to take a snapshot of the screen with the speaker and the chair and all the participants. Lorenzo, would you please, switch off your presentation, stop your presentation, and we'll take a screenshot. Thank you. Thank you. So is it done? Okay, thanks to everyone. Thank you, Lorenzo. Thanks, Anibanda.
Yeah, okay, thank you.
Yeah. So we are closing this session. Yeah. Bye, Lorenzo. And we'll meet again at 8:30 for the evening session.
Okay, thank you.
Hi, Murthy.
Hi, Minhas, how are you doing?
Yeah, I'm good. I'm good. So you have been changed. Huh? So we are waiting for participants to join. We'll start sharp at 8:30.
Sure. Yeah, take your time. How are things?
Yeah, it's okay. You are the chair now in the department.
Yes, I am.
Oh, so there are lots of pressure now. And
Yeah,
today is the last day of March meeting. I think.
yes, it is. Yeah, this week has
Yeah.
been extremely busy because of March meeting.
Mhm.
So my students were giving presentation, and there are a few other presentation of my collaborators and things. So this has been just a crazy week. Yeah. How are things with you? How was the? I mean, today is the last day of the
Yeah,
webinar,
today is the
right?
last day. It was good, quite good.
Oh, veteran, nice.
Yeah. Are you acquainted with Bhaptosh? He's also from IISc Bangalore.
Sorry, who?
Bhaptosh
Both?
Bansal. Bhaptosh Bansal.
Yeah,
He's
I know him.
yeah. He's in IISER Kolkata. He gave a nice talk on high magnetic field PL.
Oh, good. That's good. Yeah, I did when I was in IEST, like you remember in 2013. So
Yeah.
I did give a
Okay.
talk in Calcutta, and I meet. He just joined, I think, at that time, Bhavtosh. Yeah,
Yeah.
yeah. His lab wasn't ready, but I remember meeting him there. Yeah.
Yeah, he has made a very nice laboratory with almost indigenous things.
Oh, very nice.
Batteries from Pune and all these things I've bought here.
Oh, that's nice. That's nice. Yeah. Should I be sharing my slides? You want me to, or?
Yeah, you can check. You can check. Shweta, will you stop your presentation?
Okay. I don't use Google Meets. I have to see. Yeah, present now. Yeah.
There is a small trick. After present now, you have to select the whole screen, entire screen.
Oh, you have to see the entire screen. Okay. Entire screen. Okay.
And then you click on the tab.
Okay.
Then this share option will be highlighted.
Okay.
Oh, Bhaptosh has joined. Hi, Bhaptosh.
Yes.
Yeah.
Yeah.
Hi.
And then I should be.
You have a nice beard, Murthy.
Hey, Gautam, how are you?
Yeah, I was talking about that.
But can you see now?
Yes.
Can you
Yes,
see my talk?
it's in slide mode. Yeah, now it's in full screen. It's okay, Murthy.
Okay.
It's fine.
Yeah. I don't see any participants though here in this mode, right?
Yes, only 15. Yeah, we have. Oh, we'll not be able to see. Yeah, we'll not be able to see.
Okay. Okay, let me.
We are streaming this screen through YouTube. Live streaming is going on. So all the participants are watching through YouTube.
Okay.
In our IIST live channel.
Yeah. I mean, I don't see you now in the full screen mode. So, let me know when I can't see anyone. So just let me know when to start or what you want to do.
Yeah. We'll see. Also, the chair, Professor Tapabrata Shom has joined. He's from Bhubaneswar, IOP Bhubaneswar.
Hey, Bhavtosh, how are you doing? How are things?
Yeah, okay. Good. Yeah, we should catch up sometime. Yeah.
Yes.
Nice to see you.
I was just telling Minas that when I was there in 2013, I stopped by, and then you had just arrived there, I think.
Yeah, it's been quite 8 years actually, a long time. Huh? It doesn't seem that long.
Yeah, that's correct.
Yeah.
Just time flies. Yeah.
Yeah.
So let's wait for 3 more minutes and then we'll start.
Yeah, sure. Yeah, anytime when it's convenient.
Topobroto da. Topoda. Yeah. Unmute yourself, Topoda.
Yeah, I have
Your
done so.
mic is mute now.
Yeah. Good evening to all of you. Yeah.
Good evening. Good morning for me, Lord.
Hello, Professor.
We'll start the session at 8:30. Topoda.
Yeah, please. So now we can start.
After 2 minutes.
Okay, sure. No
Sharp
problem.
at 8:30. It's 8:28 now.
Sure.
We'll wait for some more participants to join here. Actually, our GSUT has a restriction of 100. Yeah. I'll introduce the chair, and then the chair will introduce the speaker, and the speech will start after that. Moushumi, the head has joined, no?
No, not yet joined.
Mosumi, wish you very good evening.
Very good evening.
Everything is fine?
Fine.
Good.
We are on the penultimate session of the webinar. Am I audible?
Yes, Minaj, you are.
Okay, thank you. So, good evening, everyone. We are on the penultimate session of the webinar. Actually, this is the final technical session of the last day of our international webinar, Advances in Electronic, Optoelectronic, Photonic Materials and Devices. We started the day in the morning with a very talk by Professor Chia Jai Lui from Changhua University of Education, Taiwan, on thermoelectric materials. After that, in the afternoon session, we had a very nice lecture by Professor Lorenzo Pavesi from University of Trento. He gave a talk on silicon quantum photonics. Now we are going to start the evening session, actually the eighth technical session of the webinar, with Professor Sambandam Murthy Ganapathy. He is actually known as Murthy. Professor Murthy is from Department of Physics, SUNY at Buffalo, State University of New York at Buffalo, USA. Murthy will talk on noise signatures in novel correlated systems. We thank Murthy for accepting our invitation and to enlighten us with his recent research work. In fact, Murthy is probably he is actually the departmental chair now. So not only that, this is the final week of APS March meeting. So in spite of all these things, Murthy has agreed to deliver a talk in our webinar. So we are really thankful to him. This session will be chaired by Professor Topobroto Shom. He is a professor from IOP Bhubaneswar, Institute of Physics, Bhubaneswar. Professor Shom has varied research interests, including ion beam induced self-organized pattern formation and their nanoscale functionalization, thin film growth and characterization, hole blocking solar cells, application of materials devices for neuromorphic computing, where he uses atomic force microscopy, and his various modes as the main working thing. Professor Shom is presently the leader of electron cyclotron resonance ion source low medium energy ion beam facility since 2012, and surface nanostructuring and growth laboratory since 2009 at IOP Bhubaneswar. Professor Shom started his research career as a research scholar in the Department of Physics at Indian Institute of Technology, Kanpur in 1991, and subsequently joined as a research associate at the Inter-University Accelerator Center, New Delhi in 1998. In January 2001, he was awarded a Young Scientist Project under Department of Science and Technology, Government of India, and continued to work at IIEST. In August 2001, he moved to IOP Bhubaneswar as a senior lecturer and went ahead to become a full professor in 2016. During this period, he has been mentor for 10 PhD students and 20 postdoctoral fellows. During his 30 long years of experience in physics research, he has published more than 200 research papers in international peer-reviewed journals and has edited a book on ion beam sputtering. He has also been the guest editor of special issues in Applied Surface Science and Nuclear Instruments and Methods in Physics Research, Section B, published by Elsevier Science. Now I invite Professor Shom to chair this session. Before this, there is a small announcement to the participants. Please put your comments in the chat box. If you have any question or query, put in the chat box. We are streaming this meeting, this lecture through YouTube. So the viewers who are watching this talk in YouTube, please put your questions and queries in the live chat box, live comment box. Our PhD students will take those questions and put in the chat box here in the Google Meet. These questions will be placed in to the chair, to the speaker. Professor Shom, please take the chair.
Thank you, Dr. Hossain. It's a pleasure to be invited for this special evening session, and it's a huge honor to chair this session where Professor Ganpati is going to speak. Dr. Ganpati is professor in the Department of Physics at University of Buffalo, New York. He did his PhD from Indian Institute of Science, Bengaluru in 2000, and he did his postdoctoral research at Weizmann Institute of Science, Israel from 2001 to 2004, and National High Magnetic Field Laboratory, Florida and Princeton University from 2004 to 2006. His research interests include physical properties of low-dimensional condensed matter systems using advanced nanofabrication techniques and low-temperature transport measurements. He was awarded by Sir Charles Clower Postdoctoral Fellowship, Weizmann Institute in 2001-2 and NSF Career Award in 2009. He has published more than 50 publications in reputed journals, including Physical Review Letters, Physical Review B, etc. And his today's talk title is Noise Signatures in Novel Correlated Systems. A very warm welcome, Professor Ganpati, and now I would like to request you to deliver your lecture. Thank you.
Thank you, Professor Som, for a very nice introduction. And I hope it's clear that everybody can see my screen as well as can hear me clearly.
Yes.
Okay,
You are audible and visible.
Everything is nice. Yeah.
All right. Thank you. Yeah. Thank you, Professor Som, for this nice introduction.
You are welcome.
Thanks to the physics department at IIEST Shibpur for actually inviting me to give this talk. I had been there once about 8 years ago, and it was a very nice time that I spent a couple of days. And this relationship actually started when Minus actually visited our department as a visiting professor in 2012 and 11, I think, right? And thanks to the head of the department, Professor Mukherjee, for this invitation, and also to Minus and the organizing committee for actually inviting me to give a talk. This has been a crazy week, as Minus mentioned. This is the annual American Physical Society March meeting. So there's, I don't know which number of the talk this is. Actually, it's just blurred now. There's been talks all mornings, all afternoons, and and all of these words over the last several years. And so let's start with something simple, right? Let's look at the table that I have here. And if you think of neon, we know has 10 electrons in its atomic structure. And so if you see it's 1s full, that's 2, and 2s full, and 2p is also full. All of the 6 electrons occupy this 2p x, 2p y, and 2p z orbits, and then they're all full, right? So it kind of makes it very clear and very easy to understand that this element, which is neon, is not going to be chemically active. It is also not going to be easy to take an electron out to form a bond, let's say, or to form a compound in some way, right? Now think of the one that's just above that in the periodic table, which is sodium. Sodium has 11 electrons in its atomic shell, and you can see the last electron, which is in the outermost shell in the 3s orbit, it's a single electron, and so it makes it easier for this electron to make compounds, right? It can either share an electron, or it can borrow an electron, or there are several ways bonds can happen, right? Chemical bonds can happen in several ways. Or in other words, sodium has one free electron that can be useful in understanding the material properties. And it's also size-wise. If you look at the size-wise, if you look at the wave function of the electron in the 3s orbit, right? So the ions and the core electrons in sodium occupy about 15% of the volume, whereas the wave function of the 3s is much more than 80%. That again tells you, if you just only study that single electron, what it is doing, and how is it, like, the kinetic energy of it is much larger than the rest of the Coulomb interaction that we can talk about charge carriers. So this tells you that if we can understand the outermost electron's properties, it already tells you a lot more about how this material is going to behave. And so that's why we treat this outermost electron as, like, based on the kinetic theory of gases kind of an assumption, what we call as a Drude model of electrons, right? The Drude model of conductivity. So it makes it easier for us to understand this material and also its properties, and also how it forms compounds with other materials, which is, and if you look at the periodic way in atoms are arranged in a lattice, so then obviously this gives rise to the band structure or the band theory of materials. And so far, we could conveniently ignore the interactions of this one outermost electron with any other electron, right? With any other electron within the same atom, or any other electron in other atoms, or even the positive charges in the nucleus or the ion core in total. So we can ignore all of these. We can ignore even the vibrations of the atom that gives you the electron phonon interaction. All of them are so good so far, right? If you go through the free electron Fermi gas model, simple things like specific heat, thermal conductivity, electrical conductivity, all of that can, of a simple metal like sodium, can be fairly well explained by these free electron Fermi gas. But that's not it, right? We all know that that's not where solid state physics ends. So take, for example, just a slightly more complicated structure, right? This is cobalt oxide, and it's a transition metal oxide, and then it forms in a rock salt kind of a structure. And if you look at the number of atoms in this compound, you will also see that it has an odd number of electrons in its outermost shell, but then it's naturally intuitive to think that it has an odd number of electrons. Will this electron be considered similar to the sodium's outermost electron, or will this metal, or will this material will also have metallic properties, right? So as like, just like sodium, or can we use the simple Fermi Dirac kind of distribution of electrons, or Fermi functions and everything that we know, and can we consider this to be a simple structure with one electron or an odd number of electrons in the outermost shell that contributing to fairly correctly like a metallic kind of a behavior, right? So what happens is that, life is not that simple. And so this is not a metal. Even you try to measure this, this has an extremely high resistivity, this compound, and it's an insulator. So where did we do wrong? So what all we assumed originally, right? So the interactions between the electrons and the ion core, or interactions between electron and the vibrations of the crystal, which we call as the phonons. All of them were ignored. So these electron, phonon, electron, ion, all of those interactions are extremely critical, and they affect the properties of these materials profoundly. Just one step further, this is like 2-element compound, right? Now think of much complex materials that you have in our life, and obviously they are all going to be subtle variations of the interactions between electron, phonon, and so on. So that's going to dramatically affect the macroscopic phenomena that we see in these materials. Okay, so I have summary of one particular example, which is a metal to an insulator switching or a transition, right? And I had also taken in this graph here examples of oxide compounds that actually show a switching between a metal and an insulator. What is a metal or an insulator switching, right? Look at this one. Let's say we have a material and then we measure the resistance of this material. What dimension is it, like a 2-dimensional, 3-dimensional, 1D? We don't have to worry about it at this point, right? So we just measure the resistance of this material. And if we can use an external stimulus, like for example, change the temperature or change the electric field or date the structure, inject charges into this material, or shine light on it, optical excitation, or magnetic field. You apply a large magnetic field, then you can switch something in the system, or even simple things like strain or stress. Take a 1-dimensional structure, pull it along the linear or uniaxial direction. So any one of these, if this material is closer to a phase transition, and we can trigger this phase transition by one of those external means or external stimulus, then it becomes very interesting to study this material, both from the fundamental perspective of understanding exactly what is driving this transition, and the second thing is what can this switching be used for in real life, right? So now come back to this one, and you can see, let me try to see whether I can use it as a pen. All right. Okay, yeah, you could see there are many oxides here, and their transition temperatures are marked. And you can see, there are vanadium compounds here. There are these, lanthanum cobaltates. There are titanium compounds here. And I would actually be talking a lot more about this neodymium nickelate compound in a while. So you can see there are all of these oxide. I only chose oxide materials. There are other things also, but I just chose oxide to give you an overview. And you can actually switch, depending on which material it is. You can switch from an insulator to a metal at any temperature that you would want, somewhere around like 60 or 70 Kelvin here, all the way up to about 1000 Kelvin. So that's a wide variety in temperature. That this is only thermal driven, right? This is only thermal driven. And look at the examples that are shown here. These are examples. This is from vanadium dioxide that tells you that you can switch from a metal to an insulator at about just above room temperature. And this is a manganate system that you can apply a high voltage and then switch the resistance by several orders of magnitude between metal to an insulator and back. We will talk a lot more about these electrical and thermal switching on different materials as we go along. And there are other ways, like this is it's a vanadium compound. You can see uniaxial strain can actually make this system go from being a metal to an insulator. And this is magnetic field here, and this is just pulse laser kind of a measurement. So this just gives you an overview that in many of these oxides, there are two competing phases that are close by. And it's not that difficult to use one external stimulus to make the switch between these two ground states, right? That's a message from this slide. And now, what can we use that, right? There are many kinds of insulators, we know, which is like band insulators, Mott Hubbard kind of an insulator, or Pearl's insulator, or Anderson insulator. There are many kinds of insulators. And if we can utilize these materials to use one stimulus, like external or internal, right? When I say external, this could be temperature, magnetic field, electric field, and so on. Internal is actually taking one atom from the crystal structure and putting another atom, which could give you a different kind of an internal pressure, chemical pressure, that could also be helpful in switching. Or in other words, doping, right? In semiconductors, doping is very commonly known. And even in these oxide and other complex materials, doping has become very useful method to actually tune properties, right? And while doing all of these, what do we expect to get, right? There are many myriad applications that you can see. I just put some of them here. This is a very nice review that came about 10 years ago that actually summarizes these applications of these metal insulator switching. But you can see already you can use it for hysteretic, memoristic, or memory devices, as well as understanding fundamental Mott physics or thermal switches, because thermal switches is a no-brainer. We could already see that you change the temperature, material that shows this switching can be useful, and tunable materials also in metamaterials, all that. There are many applications, but the basic thing that we need to do before applying these materials for these applications is having a better understanding of the fundamental behavior of these materials under different conditions and under different stimuli, how these stimuli switch these materials, and what exactly is happening at the microscopic level, right? So that's the main thing. So just as a what we do in the group, we work with the many groups that actually grow these materials. We are a measurement side of the projects. There are collaborations that we have with the many groups that actually grow these materials. So what we are looking for, there is a general theme about what exactly we are looking for in all of these materials. We are looking for single crystalline, extremely pure materials, and we take a single crystal of those in different forms. Some materials are pulsed laser deposition, few units of thick films. Some are single nanowire of a single crystalline material, or some of them are crystals of just single crystals, right? And so look at these examples we have worked on. This is vanadium dioxide, right? Or these are like silver doped vanadium pentoxides, or bronzes, vanadium bronzes. And also these are there's nickelates. We worked on neodymium. We are currently now working on something with the European doping on these. And also like not oxides, completely different, like copper iridium sulfate, which is it's a very nice spinel compound. I'll present, I would not go into all the details of all the materials, just as for the shortness of time, I would pick two examples. One is this neodymium nickelate and this copper iridium sulfate that we have results recently from over the last few years. And I just want to mention here also that this is something really interesting. We haven't made a lot of progress on them yet, but they looks very promising. These are these V2O5 structure, which are bronzes, but you have silver doped onto them. But depending on which site the silver takes, these oxides actually can form tunnel structures, which makes them very interesting. Like here, you see these are all the tunnel structures of silver line going through, which make them very interesting because you can actually do local doping from the AG site onto the V2O5 bands, and that makes them really tunable materials, right? And also you can do one full layer of AG. These are like chemically doped into the structure. And so this makes it easier for these materials to be peeled, just like graphene, into two-dimensional sheets of AgV2O5 as well as V2O5, which is again something that one of my graduate students is currently working on. But we still have a long way to go there. So I am not presenting the results from that yet, right? So okay, so yeah. So what do we do? So again, this is a general theme. There's small differences between each one of the projects that I would present. But the idea is that we get the material in forms of like, nanowires, like you could see a bunch of nanowires, or in terms of two-dimensional, crystals that are grown on a particular substrate to have a lattice mismatch and things like that that can be engineered at the interfaces. And so we take these single nanowire, for example, you take one nanowire out and then you make electrical connections to them, right? You can see here. Or if it's a two-dimensional single crystalline film, you make multiple electrical connections to them, and to study transport properties, which will look like this. We send currents, measure voltage, of course, do it carefully because they are really thin, small samples, so you can easily blow them. And so you do electrical conductivity measurements at a different stimulus, like temperature, magnetic field, voltage, and so on. This is the generic idea of all the measurements that we do in my group, right? And you could also see, I'm not sure how the contrast looks on your screen. You could also see, you could image these, formation of domains and things within these materials in a nanoscale. So we also did, I'm not going to present more results on that, but we also did simultaneous transport as well as noise measurements when these domains are being formed, which you could actually watch, and as you're looking at them through high resolution microscopes, right? So the idea is like, and I'll just summarize my introduction part of it in a little bit, is we have correlated systems that are not simply explainable using our Fermi kind of a description. So we take the purest form of these materials, like single crystalline, single isolated nanowires or isolated thin films, and measure electrical transport as well as noise spectroscopy. I'll explain to you in a minute what noise spectroscopy is. And the first example I'll show you is about rare earth nickelates, right? So these are transition metal oxides. And what makes them interesting is that there are two phase transition in these materials. One is metal insulator transition. These materials go from a paramagnetic metal to a paramagnetic insulator at a well-defined temperature. And at a lower temperature than that, there is also a magnetic needle transition that happens there, right? So if you look, this is an example of just to show you how the metal insulator transition looks like. You can see that at room temperature till about 200K, this is a very good metal, and then there is a transition, and then there's a very good insulator here, and there is a region in between where there is things happening, and depends on what kind of a rare earth ion you take. It could be, I will present results from neodymium, but you could see that depending on what rare earth you take, you could actually tune this metal insulator transition. For example, because the radii of the rare earth ion changes the properties of this compound, right? So neodymium, you could see the transition, the metal insulator transition is about 200K, which is what you have here, right? So, and there is another thing you could do here. Okay, just before I move on, so I have to mention this. What actually happens at the transition is that these octahedras in their crystal structure, they twist and turn. So that opens up a gap in the band structure, which is what gives you this insulating phase. Okay, so another thing we could use in these material is actually strain. Okay, so in bulk, you could see how the choice of your rare earth ion changes your transition temperature. Now, they have all of these materials, they have a crystal structure. There is a lattice constant. So if I grow these on as a film on a substrate, then I can do a few things. I can do the film as well as the substrate to have the same lattice constant, which means there will be no strain or stress on the film, or I could choose the substrate in such a way that it can either put a tensile or a compressive strain on them. And it was also shown, about 20 years ago, that you could use these lattice mismatch between the substrate and the film on these rare oxides, that that obviously will actually play a role in determining your band structure and hence your metal insulator transition. So this is the summary of some of the films that we have worked on. Is that if you look here, this is when this is all neodymium nickelate, okay, NiO3, right? And if I take a substrate that has exactly the same lattice structure as the film that I'm growing on top, which is the neodymium nickelate, then at a zero lattice mismatch, you basically, the material is a film. It's a metallic film, is just not showing any phase transitions or anything. And there are some questions about what kind of Fermi liquid or non-Fermi liquid kind of a behavior in these temperatures and all that. But what's interesting is that if you actually go to the tensile side of the strain, that is the strain, again, remember, these are extremely thin. They're only a few unit cells, right? So the lattice mismatch between the substrate, which is again a single crystalline substrate, and on the film on the top can have profound effects on the entire thickness of the sample because they're very thin, right? They're ultra thin films. So if you take this lattice mismatch to be, let's say, 2%, right? So you basically have a film that has these antiferromagnetic insulator to a paramagnetic insulator to what happens here. Here it's a paramagnetic metal and so on. So you could choose what your substrate is and how much of a mismatch of lattice that would provide to the film that is grown on the top, and engineer the phase transitions in this way. And so we worked with 3 films, and I will just present one example of just only one film here. We chose 3 films that are marked with these vertical arrows in this picture right here, and with 3 different lattice mismatch that are engineered to grow in such a way that they have these phase transitions that can be mapped. So these phase transitions were mapped by thermodynamic measurements like magnetization and specific heat and everything. So our idea is to measure transport in these materials to see what exactly happens at these phase boundaries. Is it a clear transition from one phase to another, or there are like domains that are being formed? Because the formation of domains, for example, is extremely important as we go to smaller dimensions, as well as try to do devices out of these materials for switching. Because there is an inherent uncertainty that comes with the multiple domains being formed, and then transport becomes percolative and things like that. So a clear understanding of exactly what is happening is important. And there are a few ways that you could do. One is noise spectroscopy, and another is also scanning the samples with like things like STM and all that. But they are tiny, small area kind of an effect, right? I mean, STM can do tens of microns and things, but not giving you a full range of what's happening with the macroscopic size of a full device, which is what is needed for applications, right? So, okay. So just to remind you what you would see in these materials. So as you start cooling the sample from room temperature, the sample is in a paramagnetic metal phase, and right about closer to 150, just below 200K, the resistivity start to increase rapidly, and the system enters into a same paramagnetic phase, but insulating. And at further low temperature below 100K, the system is an antiferromagnetic insulator. So this is for all the 3 different devices with the different lattice mismatch that I talked about. All of them summarized just in one slide, just the raw data. But remember, I'm going to just focus on one of the example. And so I'm going to pick one of these and then study the transport. Before I do that, what am I going to do? I showed you some simple transport measurements, but I'm going to sit and then measure how the scattering events in these materials work, or what can we understand about the scattering of the charge carriers within these small thin films. Okay, to understand that, we need to know what are the noise that I'm going to talk about. Right? You take any material, take a piece of copper, right, a piece of aluminum, and just measure the electrical resistance as a function of any parameter that you want to do. Let's say we fix temperature, we fix everything else, just room temperature, take a piece of copper you send current and measure the voltage drop across the material, right? So it will have whatever the temperature and whatever the resistance is, that will have an effect on what we call as the thermal noise or Johnson's noise, which is frequency independent. And the example I chose is copper, so there is no real short noise that I'm going to be doing unless I go into the low temperature, small, kind of a nanoscale regime. Short noise comes from the discreteness of the charges, which is electron in this case. And the third and important thing that we will be looking at is the flicker noise, which is frequency dependent and has a 1/f frequency dependence. And that exponent alpha will also have some interesting effects that we will see in a moment, right? So if you look at it, the thermal or the short noise will dominate at certain frequencies. At lower frequencies, because this is 1/f, so at lower frequency, the power spectral density of the flicker noise goes up. So it will be easier for you to measure what happens at lower frequency, this flicker noise. And two things we can learn from it. One is the magnitude of this noise, and the second thing is the magnitude of the power spectral density and the exponent. We will use both of them to learn more about these materials. Okay. Why do we want to study this noise in this? Okay, as I had mentioned, these transitions are not very clear. In bulk, they have been studied very well, but when you actually put in these lattice mismatch that gives you an inherent tensile stress in this sample, it is not very clear how the sample is going to work. Are they going to form puddles? Or are there going to be some domain formation? Are the domains going to be pinned? Are there going to be depinning transitions within the domains before a metal to an insulator transition? There are many relevant questions here which are not well understood, right? And you can also think of examples where noise has been used very commonly. Domain wall motions in nanowires of any magnetic materials, charge density waves, as I had mentioned, structural transition. There are many examples of how the study of these fluctuations within a measurable quantity. In our case, it's a conductivity. So how do we measure, right? We measure basically a voltage as a function of time. So it's simpler said than done, right? So think about it. When I'm measuring a resistance, I just fix the temperature, let's say, and then the resistance has, let's pick a value. Let's say it has 1 kilo ohm. Okay? And when I say 1 kilo ohm, that's a macroscopic measurement of the resistance. It's not exactly 1.000000 kilo ohm, right? There are fluctuations of the resistance, random fluctuations as a function of time that come from the scattering events that happen within the sample, right? So I need an extremely sensitive measure of the fluctuations if I'm interested in the statistics of those fluctuations. And so what is the easiest way that you want to measure a quantity that is 1 part in, let's say, a million, or 1 part in maybe a billion, over a background that's like of the order of, like, let's say millivolts or microvolts and so on. But I'm trying to measure like really nanovolts or much smaller than that. So we use a Wheatstone bridge circuit as shown here. So the sample becomes one arm of the bridge. So under balanced conditions, what the bridge measures is only the residual fluctuations, because the mean is kind of balanced out, and physically removes the mean, and also using a lock-in amplifier provides you the sensitivity that you would want to get of the fluctuation. And each one of the measurement, I'll show you later, gives you how long each one of the measurements is, somewhere between 33 to 66 minutes long. The reason we chose those numbers are because the longer the measurement gives you lower in the frequency range of interest, larger range of interest that we are interested in. But there is a problem, right? You want to keep measuring for, let's say, an hour, every parameter that you're trying to control. You're trying to fix the temperature, you're trying to fix the magnetic field, you're trying to fix the voltage, everything is measured. You're just measuring only the fluctuation. So all of those cannot drift. You need to have much better than millikelvin accuracy of your temperature control. And magnetic field and voltage are easier to control, but temperature, for example, it can drift by a few millikelvins here and there. So all of them become extremely critical while doing the measurements. And then we do non-analog filtering to avoid interference from other electrical. These are electrical measurements, so there are a lot of interference, just like cell phones and someone starting a pump in the next room. There are so many interferences that we need to avoid. And also, finally, acquiring is also a challenge, right? You see here, this is how the signal looks like. The signal is the noise, right? So this is the residual fluctuations when the mean is subtracted over a function of time, right? You could see that the general way an experimentalist would do measure these fluctuations and collect the data in a computer is using what we call as the GPIV, but those are very slow. You can't use them. And a lock-in, we can't store everything in a lock-in because the buffers are too small too. So we use an analog to digital converter that actually converts the signal and then stores them, and they look like this. Okay, they look like completely random fluctuation. That's what you want to see, right? Completely random fluctuation, but they have information that I'll show you how they are useful. Okay, and of course, after we analyze, we do a lot of digital signal processing to actually take any kind of power line interference, and power line in the US are at the 60 hertz and sub multiples of it and then multiples of it. So we need to avoid those interferences to get rid of it so that we get only the signal from the sample, right? And then we do look at the data in two domains. One is time domain, where we do some digital signal processing and process what we call as the probability density function. I'll get to what is probability density function in a couple of slides from now, okay? And the probability density, we just use one method, but there are many statistical ways of actually calculating the probability density function. And the second one is in looking things in the frequency domain. After acquiring the voltage as a function of time, you take basically the Fourier transform of that data that gives you the power spectral density as a function of frequency. So we use different methods. And the second spectrum, I'm skipping the second spectrum for this talk, but we also look at the spectrum of the first spectrum, but we'll look for the time that we have here. So I will leave that out for the time being. Okay. So yes, so let's look at the data. I showed this graph earlier. So you have, I just picked one example here. So you have a metal to an insulator transition here. I'm going to say are these three vertical lines that I have here. One in the completely metallic phase, one in the transition regime, and one in my antiferromagnetic insulating phase. I sit at those temperatures, fix the temperature, measure voltage as a function of time, take the Fourier transform of it. So I will be getting the power spectral density as a function of frequency. And that's how it looks, right? And this is the PSD, or the power spectral density, as a function of frequency. Remember, this is the flicker noise. So I'm looking at a very low frequency or large time scale events that are happening. Any higher frequency that you go, obviously the thermal noise will start to play a role. So we are avoiding that high frequency part of it, right? So you could see when the sample is in the paramagnetic metallic phase, in the full entire range, 4 orders of magnitude of measurements, the power spectral density, it's a power law because it's a log-log plot. So the linear line here is the power law. So it has a single power that actually fits the entire temperature range. Now, once I go to the insulating phase, you could see that there is some kind of a counter frequency here where the spectrum changes slow. Or in other words, I mentioned there, right? The power spectral density goes as 1 over f to the power alpha. That alpha changes from one frequency range to another. So let's summarize that in this one, right? So if I plot the power spectral density as a function of temperature at two different frequencies, I just picked two different frequencies, one lower frequency and like somewhere here, right? And plot this again. Let me just give you how hard it is to measure this. Okay, each one of those data points that you see is an hour, right? You sit at that temperature and then we collect the time dependent voltage fluctuation data for an hour. Okay, that's 1 hour, and then we repeat it 3 times. So to average, just to make sure. So each one of those data point is like 3 hours of data, and this whole graph is probably about like a month or so of measurements. And this tells you that for graduate students in the audience, right, it tells you it's not just the knowledge and hard work, it's also the patience and perseverance that helps you to get good quality data during your PhD, right? So if you look at the two different frequencies that I've picked and look at the part spectral density as a function of temperature, the high frequency part, there isn't really much happening, just slowly varying function. But the low frequency part, you could see only when you enter into these insulating phases, there is a couple of orders of magnitude increase in the part spectral density, or the noise magnitude, as you call it. And the slope changes you could see already here, and the slope changes captured here. The alpha is captured here. At the high frequency part, it's just flat, but at the low frequency part, the slope changes from 1 all the way to about slightly more than 2, right? So this is two things that are clear. There are some interesting violent events that are happening in this region, right? When the sample goes from metallic entering into this paramagnetic insulating phase, the noise magnitude, or this comes from the scattering events that are happening in the sample, rises by 2 orders of magnitude. And eventually they also come down as you go further into a homogeneous insulating phase. So what can be the source of noise for these materials, right? Obviously, the high frequency part is just monotonic decrease across the temperatures. Those are just, there are defects in these samples, even though they're single crystalline films, there are defects in these. The thermal activation would give you such a slow varying function. But the low frequency part is an interesting thing that tells you that when you actually slowly vary the temperature, as you're coming closer to the other phase, domains of opposite phases are actually forming, and then it becomes a violent playground, right? So it becomes like there is domain nucleation and domain interaction and domain growth. There are many events that are happening that can clearly give you much higher noise level, as well as a slope value which is away from 1, right? So the second way of looking at it, okay, so we have these, some idea that something's happening near those phase transitions. Let's look at the time domain. So, it just basically, it's a histogram that tells you which fluctuation occur more. Obviously, that are closer to 0 should occur more. Look at the example I'd mentioned. If you take a piece of copper and send a current and measure the voltage, the residual voltage fluctuation as a function of time, and plot that as a probability density function, it'll look a perfect Gaussian like this, right? Because there isn't anything that is going on, because an independent random fluctuation will give you a Gaussian distribution. Whereas non-Gaussianity can occur for several reasons. Let's not worry about what are the reasons yet. Look here, in the paramagnetic metallic phase, I'm plotting the probability density function as a function of, this is the residual voltage fluctuation. You could see that everywhere in the paramagnetic metallic phase, the blue is the data and red is the fit to a Gaussian function. It's fairly well, fit to the Gaussian profile here. And now let me move to the transition region right here. When I move there, I can't fit this to Gaussian anymore. This is non-Gaussian, as well as, there are no shapes. There are different kinds of shapes at different temperatures and so on. Now I move well into this antiferromagnetic insulating phase. There I see something interesting, which I will not talk more about, because the idea of this talk is not to go into the details of one particular material. You could see that it's complete breakdown of non-Gaussianity, giving non-Gaussian double peak kind of a thing, or some Gaussian features are there at some temperatures. So it just basically the system switches between these two, Gaussian and non-Gaussian, well into the insulating phase. That's actually a very interesting thing that we noticed, and then we kind of understood that from coming from the 2 nickel sites that are present in the sample. But let's leave that aside for a moment. Okay, so just want to conclude the first part of the talk, and then I'll give you a few minutes of the second part of it. Is that very close to the transition, noise magnitude dramatically increases by a few orders of magnitude, and also the fluctuations are non-Gaussian, and quite likely they are correlated. So it gives you an idea that there could be some mod physics in it. Our next step is to actually get these materials with get these materials with some high K oxide, so that we could inject charge carriers into that to be able to generate some mod kind of a transition into those materials. And the second example I wanted to show you is actually another material, which is copper iridium sulfide. And again, there are many things that are happening in this material. So we are actually sitting, there's a rich phase diagram of these materials when you dope them with chromium, but I'm going to leave that aside for a moment. We are just sitting with 0 chromium, which is right along this transition, along this, right? So it has a diamagnetic insulator to paramagnetic metal transition that are happening around 230 K. So again, you can see the resistivity as a function of temperature. There's a huge change of resistance from a metallic phase at high temperature to an insulating phase at low temperature. But what is more interesting in these is that, let's say I sit in the insulating phase, let's say, right? If I sit in the insulating phase and if I send a non-equilibrium kind of a voltage, that's of the order of a few volts, the system switches to a metallic phase. Right? So I can, in addition to this thermal switching that happens, I can also electrically switch this material, right? That's interesting. And also the question is that what exactly is the parameter that is responsible for electrically switching this and thermally switching this? So we tried, this is a collaborative project with our theory group, who actually developed a model for this also to understand the electrical switching. So I'll present both of those results in a few minutes. So first, obviously, the thermal driven metal insulator transition. You could see that going from 330K to about 150K, you could see this big switch from metal to an insulator. And if you measure the residual resistance fluctuation, either voltages or resistance over the mean resistance as a function of time, you could see that in the metallic phase as well as in the insulating phase, the magnitude of fluctuation is extremely small. They are just offset for just clarity, and but they're all the same scale. So, but in the transition region, you could see that there are violent events that are happening. Even in your time trace, you could already see them. And you take the frequency domain, which is the PSD, power spectral density, just like what I showed you in the previous slide. As a function of frequency, you could see that in the metallic and insulating region, the slope is of the order of 1, whereas in the transition region, both the magnitude has increased as well as the slope has changed. Summarizing that, you could put them in here, right? So again, this is power spectral density as a function of temperature. This is just the slope as a function of temperature. Both of them have similar features. You could see they're all, low noise magnitude, well into this two ends of the transition. But right around the phase transition, there is a, 4 orders of magnitude increase in noise. Similar story as the previous material. So, but there are also some subtler details which I'm ignoring for the time being, is the asymmetry of the transition and everything. But I will skip that for the moment. We'll be happy to talk more about it if there is interest. And okay, so then we did work with our collaborators on trying to simulate this. Right, we took a non-equilibrium free energy model based on Ginsburg-Landau kind of a formalism. And you take the order parameter, which is the energy gap, and take that to be the fluctuating variable. And then you also calculate an effective temperature, which you make sure that you take into account, you're applying a non-equilibrium voltage. So you want to make sure that the sample is not being heated, or, to put it better way, you want to know how much of the heating that is happening there. And then you take a random resistor network and then generate the time series of fluctuation, as well as compare them to the experimental. So this compares the experiment and theory. You could see these two. That will kind of captures most of what you want to see. And these are all, again, repeats of comparison of experiment and theory. Just for brevity of time, I'll just only show you here. In experiment, you could see the metallic and in insulating phases are very calm. And in the transition region, so many things are happening violent, and which is reflected in the power spectral density here. And in voltage thing, we found something interesting too. If you're so far away from transition, let's say, somewhere around here. When you apply voltage, then the current voltage characteristics look like this. When you apply the voltage, it's pretty linear till about here. Non-linearity starts here, and single domain jump into the metallic phase. And you can also see it in the differential, which shows the single peak, right? But if you come closer to the transition, let's say we are sitting here, right? The jumps are multiple, right? So, and if you measure noise, if you have a single domain jump, the noise is flat in all the voltage ranges. Whereas if you come closer to the transition, there are multiple jumps, noise is violent, right? You have this, and then, right? So noise goes by orders of magnitude higher when the jump occurs. So this tells you farther away from the transition, thermal transition at temperatures farther away, the switch that happens electrically goes through a single filamentary formation or a single domain formation. Whereas coming closer to the TC, multiple domains are already formed, maybe because of, you have more thermal energy now. And the idea becomes it's not a single jump, rather there are violent events like percolation and growth and movement of domains, domain interactions, and so on, that gives rise to a completely different noise profile in these materials. And we also, from the simulation, we could also basically get the same idea. And we could also take a map of this random resistor network. So we could also take snapshots of the order parameter and see how things form. And when you come closer to TC, you could see there are already regions, right, that are have these metallic filaments, that are metallic domains being formed, and a single filament kind of a formation happens, even though you could see there are many regions, and anywhere you could actually have a path connected here. So the idea is that when you're well away from TC, the jump occurs by just one single filament formation. As you come closer to TC, multiple local domain formation will drive the transition. And this was not known in these material. So we are actually right now working on, hopefully be able to do some scanning optical image, infrared image kind of a thing. So where we can see a larger size of the single crystal sample and then map those domains. That's something that we are hoping to do as we go along. With that, I'll conclude that here. So there are these asymmetry and everything, but the main idea is that we looked at two examples and similar ideas. This is the scanning IR images that I show you from vanadium oxide. So it looks like this collective domain dynamics of puddles that are formed and what spectroscopic signatures they have from each one of those domains. They all seem to be a common thread between many oxide materials that can be potentially used for switching applications. And so complex oxides have this emergent phenomena as what actually drives these things. It becomes, there are a lot of interesting phenomena, but magnetoresistance switches, electrical switches, thermal switches, but what exactly is behind them seems to be, there's some converging ideas into what actually happens. And we're happy to contribute some to those conclusions. With that, I'll give an acknowledgement. All of these, what I presented, are work from my research group students. Most of them are, most of people who are actually contributed to these are all graduated. They're all in different positions. So Jai and Thailand, they worked a lot on vanadium oxide. She is the one who wrote the first code for these noise measurements and things. And Ali worked on this nickelate, and Adam worked on charge density waves and so on. Dasharat is the current student who will be graduating by this summer. He worked on this copper iridium sulfate, and the other two students are currently learning. And these are the students who undergraduate students who worked in the group in the just last year, but there are others who I didn't have enough space to put in. Thanks to all our collaborators who actually provide us these fantastic single crystalline pure samples that makes us actually explore physics at the fundamental level. And National Science Foundation supports our research, and I'll be happy to answer any questions, and I will stop the sharing now. Thank you.
Thank you very much, Dr. Ganpati. I think now the session can be considered to be open for a few questions.
Sure.
Professor Shom, actually, there is a question.
Yeah.
In the chat box.
Yeah. So let me read out for the speaker. The question is why the slope changes at the particular frequency in slide number 17 at lower temperatures.
Yeah. So what happens is that when you approach the phase transition, and the events that are happening are not simple independent events anymore. So in independent event, it will just have one slope, which is 1 over f with the power to be 1, right? That's what you will see in any simple resistor, for example. But when things start to happen, maybe there are other interactions, like, there are correlations that are coming into picture, mod kind of correlations that are coming into picture will make this slope go up. Why it happens at a particular frequency depends on the material. In some materials, the corner frequency is an effect that is coming from what kind of transition it is. And there is no real scientific significance to that particular value. It can happen at a few different values in different materials. But the idea that your correlations start to occur at a frequency is common in many samples.
Well, we don't have any other question in the chat box, but still, if anybody has any question, can still mention here or can ask probably.
Yeah, the previous question was asked by our master degree student, first year student, Pritam Bhagat. Now there is one more question, I guess.
There is one more question now by Sudipta Chakraborty. Please focus on the switching in IV once again. What is the change of resistance during the transition?
Yeah. So you want me to share again? Is that clear now? Can you see?
Hearing, yeah.
Yeah. Okay. So if you see, the concept of resistance is not very clear here, right? So you have to understand it is only linear in this region, right? It's linear only in this region. So there, obviously, the resistance means something. But after that, it's getting into nonlinear regime. So what exactly is happening is that you're applying a larger non-equilibrium voltage. So there are a few things that can happen. One is the electric field can give energy to the electrons, and then you can have what in semiconductor parlance, what they call as Pull-Frankel kind of a charge or charge conduction. Or in other words, you're applying a voltage that is large enough, your power dissipated is large enough that you're just heating the whole sample, right? Both can happen. So it is always, these are the two ends of the spectrum. And in a real material, it's a mix of things that would happen. You will have heating obviously becoming very critical at some voltage levels. And you will also have just simple electric field effects that are happening. What we see here is that at temperatures farther away from the transition, it's the electric field driven kind of a transition. I just want till that particular value of voltage, nothing happens, and then boom, there is a filament that forms, right? Whereas when you come closer to the transition, thermal effects also become important. So there is what you see is probably a mix of both thermal as well as electrical field induced effects. Hope that helps.
Okay. As of now, we don't have any further question in the chat box. So I think we can probably close this talk now. And I hand it over to Professor Hussain. Minaz, please.
Yeah,
thank you,
Professor
Hussain, once again.
There is
excellent to talk to listen to you. Thank you. Yeah, Minaz, please.
Yeah, actually, there is one more question, I guess.
Sure.
Okay, yeah. Is there any chance of trap-assisted process?
Yeah, there is. But we are not near any dopant levels in this material yet. But For example, we did measure single nanowires of bismuth sulfide and bismuth selenide, which are semiconductors, the N-type semiconductors, where the sulfur sites provide you those, basically the trap sites. And there we did see trap-assisted kind of a behavior as we are adding charges to the nanowire. We could see the trap-assisted behavior takes over. But in this material, we are not closer to any donor or acceptor levels. So I think the trap-assisted, at least near this insulator metal transition, is probably not relevant, but it's an extremely important point in many other materials.
Okay, that's all, I guess.
Yeah. Now, Minaz, you can go ahead. Yeah, please.
Yeah. So thank you, Murthy, for your nice talk. Thank you, Prabhupada, for chairing this session. So we are concluding this technical session now. We are going to start the valedictory session, the last session of this webinar. This valedictory session will be chaired. Oh, before we switch to the valedictory session, I request everyone to switch on their videos. We'll take a snapshot of the screen with the speaker, with the chair, and all the participants. Okay, thank you, everyone. So we are now switching to the valedictory session, and that session will be chaired by our head of the department, Professor Krishnendu Mukherjee. So, Professor Krishnendu Mukherjee, please.
Thank you, Minaj, and everyone.
Oh, thank you very much, Minaj. So the final note to be read out by me of this webinar. So in the last couple of days, we have been listening to nice talk, but the point is the final note to be read out by me. But of course, I am entrusted with this particular job. But anyway, I don't find myself suitable for this particular job. Okay, now just start the Thanksgiving note. The point is, we had a nice inaugural session on 17th. Am I audible?
Yes, Professor Mukherjee, you are.
Okay. So there the presence of our deans and our honorable director, Professor Parthasarathi Chakraborty. So we are indebted to all of them. Their help, especially our director. We are getting a lot of support and inspiration, as well as encouragement from him to make this event a grand success. So we are basically thankful to them. In spite of their busy schedule, they have come to attend this inaugural session. And at the same time, our director has given a nice talk describing the journey from our vacuum tube electronics to the modern days electronics like semiconductors and the integrated circuits. Okay, now let me just recollect what we have been listening to since last few days. The first talk was by Professor Krishna Tyagarajan. So he has discussed about the good, bad, and the esoterics of nonlinear optics. It was really a very nice talk, lucid talk, and he briefly described the nonlinear effects in optics and its vices as well as its virtues. The next talk was given by Professor Christopher Finot. He discussed about the nonlinear pulse shaping in optical fibers. He discussed how the combination of Korn nonlinearity with dispersion in optical fibers can be used to generate new temporal and spectral waveforms. So the next talk on the last talk that was given by Professor Agarwal, that was also a nice talk. I mean, he mentioned about how to map a pulse propagation equation in fiber, ignoring, of course, the nonlinearity, to slit diffraction by using the space-time duality. Right? It's a nice idea to listen to. Right? And then he discussed how the results in diffraction theory can be used for pulse propagation in fiber. In that case, the spatial boundaries will be replaced by the temporal boundaries, as a result of which the momentum conservation in case of spatial boundaries will be just replaced by the frequency conservation with temporal boundaries. So that is more of related to our idea about the quantum mechanics, as if the dual variable, I mean the conjugate of time is energy, as if so. It's really nice to hear this talk. The next day on 18th, the first talk was by Professor Sumit Kumar Roy, sorry, and he discussed about the plasmon enhanced 2D semiconductor based photonic devices. He also discussed about the possibility of forming this exciton plasma polaritons bound states in gold nanostructure layered WS2 hybrids. Right, he has given, there's a nice name for this bound state, which is called plexitons. Right, and that was really a nice talk to listen to. And in the next session, Professor Desdeep Shahadev, he discussed about the practical insights into graphene synthesis on copper using high-tech indigenous CVD that he has constructed in his laboratory. On 18th, there's another talk by Professor Shomi Mondol, who discussed about the use of optical fiber effectively for various optical instrumentations for its excellent light guiding capacity. And another interesting talk was on the 18th. Another interesting talk was presented by Dr. Bhavatesh Bansal of IISER Kolkata. He is a young fellow. He talked about the making of 35 Tesla pulsed magnet at IISER Kolkata, where he performed his photoluminescence experiments in high fields. So it was really a stimulating talks for the young researchers to make such instrument in the lab indigenous method. Right. So today in the morning session, there was a talk by Professor Chial Jui Liu. He talked about the synthesis and characterization of thermoelectric materials. He also talked about the potential application of these materials in different different aspects. I mean in producing some materials in the space research, right? Now, the after lunch talk was by Professor Lorenzo Pavesi. This is once again a very interesting talk to listen to. Professor Pavesi discussed about the quantum superposition and quantum entanglement, which were used to enable new technologies and devices. He also talked about the possibility of building quantum computer is using the silicon photonics. Now, the last talk that we have been listening to since last 1 hour is due to Professor S. Ganapati. It's really a nice talk. He has been talking about the correlated electron materials, which really exhibits the interesting electronic and magnetic phenomena. Also, he discussed about the transport and the conductivity noise measurement across the metal insulator, and he also talked about the nil transitions in series of novel correlated material. Right, it's really a nice talk to listen to. We are basically thankful to the eminent personalities who had given their consent to chair the sessions. So let me just recall the personalities that we have been listening to, like Professor P. Roy Choudhury of Department of Physics, IIT Kharagpur. On the 17th, he chaired the first session, and Professor P.K. Dotto, Department of Physics, IIT Kharagpur. Professor P.K. Dotto is also a close associate of our department since last 2 years, even more than that, I think. And we are also indebted to Professor Somnath Torkar. He's a very senior fellow, former UGC Emeritus Fellow, and former Professor and Head, Department of Electronic Science, Calcutta University. We are also indebted to Dr. Chumki Shaha, Scientist SF, Head of Process Quality and Assurance Division, Semiconductor Laboratory, Department of Space, Government of India. Also, our colleague, Dr. Chirosri Roy Choudhury, who chaired a session on 18 of the ECE department of our institute. And we are also thankful to our colleague, senior colleague, Professor Deepali Banerjee, who chaired the first session on 19th. And we are also thankful to Dr. Arindam Mitro, who chaired the after lunch session. Who is from Department of Physics, IIT Roorkee. And I'm also thankful to Professor Tapobroto Shom of Institute of Physics, Bhubaneswar, for chairing this session. Thank you, Professor Tapobroto Shom.
Thank you, Professor Mukherjee.
And we have been there are persons who have been toiling since last few weeks to make this event happen. I'm also thankful to our participants who have been listening talks in Google Meet and YouTube live streaming. Also thankful to them for asking good questions, and some of the questions were really appreciated by the speakers. And we are also thankful to our PhD students, especially Binoy, Shomen, and Shudipto, who have been working since last 2 weeks. Thankful to the members of the faculty of the department, especially Dr. Shampad Mukherjee, Dr. Monish Pal Choudhury, and Dr. Dipesh Majumdar for their help. We are also thankful to our office staff, Mr. Omyo Pal, Mr. Shajol Pal, and Mr. Ashim Das Chakraborty for constant help and support. We are thankful to Shomen Tapobroto for providing us the uninterrupted network service. Right, that is very important for nowadays. And last but not least, we are thankful to Professor Deepali Banerjee, Professor Mousumi Boshu, and Dr. Soyed Minhaj Hussain, the coordinators of this event, especially Professor Mousumi Basu and Dr. Minhaj Hussain, who have been working relentlessly since last few weeks to make this event a grand success. Without them, this event would not see its daylight. Thank you all for making this event a grand success. Good night.
So good night, everybody.
Thank you, everyone. Thanks, Manas.
Yeah.
Bye. Hi, Dr.
Bye, Murthy.
Thank you once again, Professor Ganesh, for accepting our invitation.
Thank you for inviting. Yeah, thank you. It was very nice. Hey, bye, bye,
Welcome,
bye.
Meenakshi, and thanks for this
bye.
invitation. Good night. Bye bye. Take care.
Yeah, you too.